so I guess we might as well get started. Well, this session of the Hydrogen Conference is devoted primarily to the discussion of methods of production of hydrogen and storage. The afternoon session will be primarily devoted to transportation issues, although if time permits, we can expand this morning's session somewhat because the scope of applications for using hydrogen is really vast. There's many sectors of society where we could put hydrogen into use and supplement or replace fossil fuels using hydrogen. Now we want to just give you a basic bare-bones overview of a concept called the solar hydrogen energy economy, because it is believed by many people, scientists around the world, that hydrogen could be a universal energy common denominator, that it could replace the fossil fuels which we have become so dependent upon in society today, and which the problems with using fossil fuels manifest themselves in so many peripheral problems that, and what I mean by that is, a lot of folks are concerned about oil spills or acid rain, or the fact that we go to war to defend our access to cheap petroleum. But if we could set our sights on finding a energy carrier or energy common denominator that could replace these fossil fuels, we might actually go to the core and of all these peripheral problems and eliminate them in the process. Now, what we want to stress in this seminar is the concept of solar hydrogen, producing hydrogen by solar means. Now, it's not necessarily to put all our eggs in one basket and say that only one particular solar technology, such as photovoltaics, is the only way to go, and that, until the price of photovoltaic generated electricity comes down, we can't have affordable hydrogen. There are really about a dozen ways potentially for producing hydrogen, and other solar technologies such as wind generation of electricity, solar thermal processes, using organic compounds that contain hydrogen and carbon, and getting the hydrogen out is a potential approach. But we'll take a look here at this flow diagram, and perhaps you can see some of the approaches that have been tried along with electrolysis here, which is the process that's been around the longest and about which we know the most. But there are other more obscure approaches that may be very viable and in the long run may prove to be more economically feasible than even electrolysis. Now, so if we have solar energy, the problem up till now has not been necessarily how to capture solar energy, but how to store solar energy and distribute it. Because by its very nature, solar energy is intermittent. It varies from day to day, it varies from season to season. It's concentrated in some parts of the globe and not others. And so it doesn't necessarily match the needs of consumers. So what we need to accomplish is to produce hydrogen and store it and then distribute it. Now, there are techniques and strategies for harnessing solar energy and converting photons into electrical energy. For example, photovoltaics, or solar thermal processes like Stirling engines mounted at the focal point of parabolic dishes, or like the Luz plants in Southern California that produce currently most of the solar generated electricity in the world today. And wind generation of electricity is one of the most affordable methods right at this point in time. And the price keeps coming down in terms of, it's down to maybe 7 cents a kilowatt hour, and they project in the near future it may be down as low as 5 cents a kilowatt hour and competitive with, fossil fuel centralized power plants. And then there are more direct processes using thermal energy to actually break down water into its component parts, hydrogen and oxygen. And Walt Pyle is here, and I'm sure he'll have a lot to say about thermolysis, using extremely high temperatures to break down water. There are also thermochemical approaches towards producing hydrogen, which involve using multi-step chemical reactions and recycling some of the reactants over and over. And it involves splitting water and getting hydrogen and oxygen out. And then there's even hybrid processes which use thermal energy and electrical energy for part of the inputs. And I can't tell you a whole lot about them, but perhaps some of these real hydrogen experts can. Now, photoelectrolysis involves actually illuminating, let's say, a semiconductor in an electrolytic solution and creating a voltage potential. And so this is like a one-step process, whereas when we discuss electrolysis here, it's really, we require a technology to convert the photons to electrical energy, direct current, and then the second step is electrolysis. So you have to consider the efficiencies of both steps to see whether or not it's worthwhile to take this approach. Now, biophotolysis is perhaps an area of quite a bit of interest, and there are ways to use organisms such as blue-green algae or other photosynthetic organisms and either create in vitro or in test tube processes where you extract components of living cells and interrupt the photosynthetic chain and steps of chemical reactions to use the part of the process in which water is split, like within living cells, and capture the hydrogen before it can be recombined with carbon dioxide to form carbohydrates. I guess in this category we would also include using microorganisms and bacteria, which sometimes can metabolize hydrocarbon materials into hydrogen, possibly using materials in the waste stream like sewage or materials, landfill debris or agricultural waste. Now, catalytic photolysis, what are we talking about exactly here? What would you consider, what kind of research has been done in that category? I mean, how is that? Huh?
Titanium dioxide aids in helping a destruction of water, generation of hydrogen and oxygen, and that would be an example of a catalytic adjunctive material on any other process. You can do it with several other systems. It's particularly effective in breaking up hydrocarbons with sunlight, UV sunlight.
Well, I was and that's done with illumination.
It is.
So that's these kind of run together here.
You can take a toxic waste or some other hydrocarbon that you want to get rid of, add rutile, titanium dioxide, shake it up, put it in the sunshine, and you'll get hydrogen off. It's a way to make hydrogen out of something that you need to get rid of.
What's the sludge left over?
Well, it also makes carbon dioxide. And if there are other ingredients such as metals or halogens, you may get a salt out of their combination as leftovers. If it isn't present in the unwanted material, if the ingredients to give you the salt aren't present, you can add whatever's necessary to keep the halogen from getting into the atmosphere, for instance. You can add sodium hydroxide and get rid of chlorine or bromine or chlorine by forming the sodium halide.
Would you gentlemen introduce yourselves so we know who really?
Okay. This was kind of thrown on me. They asked me to do the overview. I didn't know I was going to be doing this talking. I'm David Booth. I'm affiliated with Alternative Energy Engineering. I have a little hydrogen information booth over attached to that tent. I consider myself a student of hydrogen. I'm in no way an expert. These are the three panelists, the experts in the field, whether they want to be called that or not. They have as much expertise as we're likely to find in this country with the amount of research and development funding that's made available. They have done some very exciting work. want to introduce yourselves?
Oh, in turn, sure we can.
Okay.
I'm Walt Pyle from Chevron Research and Technology. I'm going to be talking to you a little bit later this morning about thermolysis, which is the one-step thermal process for manufacturing hydrogen from water and sunlight.
I'm Peter Lehman. I'm a professor of environmental resources engineering at Humboldt State University up north here. And I'm going to be talking about a project that we have ongoing at HSU in which we use electrolysis and produce electricity using photovoltaic panels and then produce hydrogen by electrolysis and then recover the electricity with a fuel cell. Be talking about that.
I'm Roy McAlister. I'm president of the American Hydrogen Association, and I'm going to be talking about the subjects that these two fellows leave out. And I'm going to answer questions. I'd really like to hear your questions, and I'll shape my comments to your areas of interest.
So each of these gentlemen are going to tell us about themselves and what research they've been doing, and we'd like to make it interactive. You can ask questions during their slide presentations. Walt has some overheads for the projector, and so you can ask questions at any time. I'm going to act as a facilitator. If things aren't flowing really well, I may, say, well, this seems really redundant and we need to move along. So I'll be the bad guy if necessary, but I don't think it will be necessary. And who wants to start?
Hello, everyone. I'd like to reiterate what David said. I'm a teacher. I'm happiest if we get a discussion going rather than me just pontificating up here.
What's your last name again?
My last name is Lehman. Lehman. L-E-H-M-A-N. And so I'll be happy to entertain your questions. You don't have to raise your hand. Just shout them out.
Could you dispel the myths of hydrogen
Dispel the myths?
Dispel the myths about hydrogen, how it's dangerous.
Well, I'll have a lot to say about the safety of hydrogen. You'll see in the pictures some of the things that we've done to make our system safe. And I think if you have questions about that when it occurs, ask me.
Do you want the lights out for your slides?
Yeah, in a minute. I'd like to begin by acknowledging the people that I work with and the person who's funded this research. This research I'm about to describe is privately funded by a man named L.W. Schatz, who is a industrialist who has a plastics company, General Plastics Manufacturing Company in Tacoma, Washington. And he is funding this work, contributing to research in hydrogen energy because he thinks it's important. I might note that I've tried to leverage his money by asking DOE if they'd like to be involved, and their answer has been thus far no. In some ways, I think that's a blessing. It is a sad comment on our society that the DOE is spending very, very little money on hydrogen energy, very little. And when I go to international conferences and represent America, it's somewhat embarrassing. I'd like to also acknowledge my co-workers. Charles Chamberlain is a colleague of mine in the engineering department, and engineering students, Ron Reed, John Paletto, Tom Perrin, and Tim Murphy, who is now with you guys.
Yes, that's right. I might just put in a plug for the type of training that Peter does. We've really been blessed by one of his former students in the American Hydrogen Association. So if you want to find someone that you can hire that does good work, look to Peter Lehman for training them.
Yeah, the story of Tim walking into Tim walked into the American Hydrogen Association asking if they had any positions, and they asked him about his experience, and evidently he had a picture of our project up on the wall. He said, "I built that."
That's right. So we locked the door.
Well, why don't we start with the slides? And I'll tell you, I'm going to structure my talk about the specifics of what we're doing. I'm not, and later if we have time, we can talk more about hydrogen energy in general and the hydrogen economy and such things. But right now, I want to describe what we're doing and how it works, some of the details of making this technology work. And the fact is that this technology does work. We can make electricity out of sunlight, and we can make hydrogen out of electricity, and we can do it fairly effectively. It will never compete with gasoline at $1.25 a gallon, but it will compete with gasoline at around $5 a gallon. In our society, we choose to do our economics, and we choose to make our laws, and we choose our political decisions in such a way that we don't use hydrogen energy. It is not because of the technology that we don't use hydrogen energy. The technology is here and it works. And a lot of these technologies may be improved upon and may make this whole thing more economical in the future, but the fact is it works now and we could be doing it now.
Do you think that it could be, if we spent 20 years investing in it, that it would become cost effective?
Yeah, well, yeah, I do. I think that using fossil fuels is going to become more expensive as time goes on, as it has. And as we incorporate the environmental costs of using fossil fuels. The cost of solar electricity and making hydrogen may get a little cheaper, not a lot, I don't think. And yeah, I think eventually those curves will cross and we'll start using hydrogen. In terms of the amount of time, I think that a good analogy is our interstate highway system. I think that changing from the energy economy we have now to a hydrogen economy would require the kind of investment and the kind of construction that the interstate highway system took. And that took about 30 years and a lot of money to build, but we built it. And covering sunny areas of this country with photovoltaic panels, if that's the way we end up doing it, which I imagine it is going to take a lot of time and investment, but sure, we could do it. I imagine about 30 years is what it would take. But,
that $5 a gallon figure was not including the environmental costs and things like that?
No, that's-
Is that just a rough?
that's a rough figure, but I think achievable. It's certainly not achieved so far. I mean, the cost in my prototype system is much, much higher than that because it's a prototype system.
But don't leave, because I'm going to show you how to make 30 cents a gallon equivalent hydrogen.
I think one other point is that gasoline in other parts of the world is $5 a gallon.
Yes, it is. And those people are much more serious about these technologies than we are. Hi, John. You want to run the slide projector? This thing doesn't work automatically.
I'll get the lights back there.
Well, this is a schematic of what we have going at HSU. This is a standalone energy system which uses hydrogen as a storage medium for solar electricity. And there is a PV array. You'll see pictures of this. There's a PV array. The array is about 9.2 kilowatts. It's nominal rating. And whenever there is enough sunlight to run the air compressor, which is the load. The air compressor is the air compressor at the Marine Laboratory. You'll see pictures of the Marine Laboratory at HSU. I'm not a marine scientist. It just was a good, convenient place to do this project. And it's the compressor that aerates all the aquaria in the Marine Lab. And we run this just as you'd run any standalone photovoltaic energy system, as you've seen examples of, I'm sure, around here. And it runs through an inverter, runs the air compressor. Whenever there is more solar electricity than the air compressor needs, which is most of the time and certainly on a sunny day, we take all the excess energy and feed it to an electrolyzer. And that makes hydrogen and oxygen. And we store them in tanks. The electrolyzer is an alkaline, a bipolar alkaline medium pressure electrolyzer. Produces gases at about 100 psi, and they are stored in tanks, 2 hydrogen tanks and 1 oxygen tank, because you get twice as much hydrogen as oxygen. And we just use regular LPG storage tanks. We have 1,000 gallon storage of hydrogen and 500 gallons of oxygen at about 100 psi. Then, whenever the sun can't provide enough energy to run the air compressor on a very cloudy day or at night, we feed the gases to a fuel cell, and the fuel cell automatically and smoothly takes over the load and supplies the electricity to the inverter and the air compressor. I should tell you right off the bat that this project is now about 2.5 years old and has been running real well, except for the fact that we don't have a fuel cell that works. And that's a long story, which I will tell you some of. Okay, next slide, please. Here's where we are. Most of you know about Arcata. When I give this talk someplace, in other places, people don't know about Northern California. We're in the northern part of Humboldt County in Trinidad. About 15 miles north of Arcata, which is the main campus of HSU, is the Marine Laboratory. Okay, next slide. There's the sign at the outside of the Marine Lab. Next slide, please. And there's the array. It is 192 ARCO modules. These are really ARCO modules. We bought them from ARCO just before. Actually, we bought them in Willis. We bought them from SES in Willis. And we bought them just before ARCO was taken over by Siemens, the German company that now owns ARCO. And so these are some of the last ARCO modules in the world. And you can see the location. It's right on the coast, on the Pacific coast. That's very scenic, and I get nice news and
How many
odds.
cloudy days you get a year?
I get a lot more cloudy days. We get a lot more cloudy days than you get here in Willits. I don't know, for those of you who know about insulation figures, it's the average insulation is about 13.8 megajoules per square meter per day. And that is a fairly cloudy climate. It's a fairly cloudy climate. A lot of fog and rain in the winter, although recently in the last drought years it's been pretty sunny there. This is not the right place to do a solar energy project if you're trying to be cost effective, but it's where I live and it's where I teach, so it's where we did it. One of the problems of being right on the ocean is it's a very corrosive environment. So if this project works well over a number of years, it will work well in other places as certainly, because this is as corrosive as it gets. Yeah.
Did you guys consider wind as a supplement? Or is it not effective?
Well, the answer is no, we didn't. Yeah, it could be. This is not as windy a location as you might imagine, even though it's right on the coast. And the fact is, it was a complication I didn't want to get into. This is complicated enough. Okay, next slide. There's a look at an overview of the whole project. This is the array. You'll see a close-up of the array in a minute. This is the laboratory building, which houses all the equipment. And I might say, you can see that this building is set up to be a demonstration facility as well. The Marine Lab gets lots of visitors. About 20,000 people a year go through the Marine Lab, which has tanks and tours available for tourists and students. And we have those windows. We now have a placard up. This was taken earlier. That explains how the system works, and we have brochures. In fact, I brought brochures. I can pass them out. There you go. These are the brochures. Let me pass those around. That people can take home with them, which explains how the project works and generally about hydrogen energy. And notice that the windows are down low. We were aiming for school children. Those are the people that are, first of all, open-minded, and second of all, are the people we really need to convince that this is the way of the future. Okay, next slide, please.
You didn't have to do any landscaping there, that was a convenient south slope?
That was a convenient south slope, and in fact, when I saw that, when I first got to HSU 13 years ago, I toured the Marine Lab, and I saw that south slope, and I said, that's a perfect place for a solar project. And sure enough, 10 years later, we did it. Now, having said that, If you ask me if I'll ever do this again, the answer is no. Working on that's a 32-degree slope, and working on a 32-degree slope was a pain in the butt. It was really hard to get that set up like that. In fact, Tim Murphy was one of the people who really put in a lot of work in getting that to be as nice looking as it is. I can say something about how these arrays work. There are 6 structures. Each structure is 2 subarrays. They're each divided in half electrically. So there are 12 subarrays in total, and each of those subarrays can be switched individually either to the load, the air compressor, or to the electrolyzer. And that's the way we control the system, and I'll show you a little about that later. This is a 24-volt system. Each of these pairs, one on top of the other, is in series, and the rest are in parallel. So we're running at 24 volts. We chose 24 volts because the electrolyzer was available in about that voltage, although the electrolyzer voltage varies somewhat. If this were a large commercial PV hydrogen facility, we would choose a much higher voltage, so we would have much smaller wires. And in fact, if I were designing this on a much larger scale, I would probably design it to run at 400 or 500 volts. 400 or 500 volts are a lot more dangerous, but on a commercial scale, it makes a lot more sense. So this is a low voltage system, but probably in the future, these will be high voltage systems. By the way, that tank on the top is a saltwater tank, which runs to the Marine Lab and has nothing to do with us.
Does the
slide, please.
electrolyzer run on salt water?
It could, but we don't. The trouble with running on salt water is salt water or seawater has got lots of other things in it, and particularly chlorine, which you manufacture when you do the electrolysis, and then you have to do something. And chlorine is an unwanted byproduct.
So will most electrolyzer systems be based on fresh water then?
My initial guess would be yeah. And all we do is we do standard water treatment. We filter it and then we deionize it. And actually, we have tapped into an old line, which again is something Tim did. We've tapped into an old line which we found running underneath our building on this very crinkly old plan. And the water that comes into our building smells like industrial waste. I don't know what it is, but we're able to filter it and it works fine. Yeah.
So, repeat that, you're not ruling out like solar distillation of seawater then?
Well, distillation is another story. Let me say something about water, and then if I haven't answered your question, ask me that. You get about a gallon equivalent of hydrogen for 2 gallons of water. And the fact is that even in a dry desert, there's enough rainfall in the year, over the year, to provide the water for a solar hydrogen facility of a certain area. So the water isn't really an issue. Not to mention that it's recycled as soon as you burn the hydrogen in one way or another. I don't know, is that what you were asking?
That's what I was getting at.
The water isn't really an issue.
Water supply to be
The water
spent
isn't
on.
really an issue. Rainwater is enough.
Who makes your electrolyzer?
I'll get to that. Teledyne makes it. Teledyne Energy Systems. Okay, next slide, please. Yeah.
What quality of water is required for hydrogen?
A pretty good water, deionized water. You pass it through a deionizing column, and it has to, for our electrolyzer, it has to be less conductive. It has to have a higher resistance than 250,000 ohms per centimeter. Which is a pretty, that's low-grade deionized water. If you're in a fancy lab, you need better deionized water than that. But it's pretty pure water, but it's low-grade deionized water is what we use.
It causes problems if it's not that pure?
Yeah, because you
just
keep.
add a little bit of acid to also tap water and you hydrolyze it, it works.
Well, sure, for a while. But if you're talking about operating electrodes for 10 years, then you can't deposit weird things on them, and you can't have deposits build up inside. So you've got to get rid of most of the things. Because you don't change the electrolyte very often. All you do is add more water. you use about. Here's the electrolyzer. It's hard to see, isn't it? Here's the electrolyzer, and everything that this is the inside of the building now. And the electrolyzer, I'll have a close-up of the module. The electrolyzer is this gray frame thing in back. And everything, the electrolyzer and all the piping, is in a hood which has plexiglass sides. Here is one plexiglass side, which is magnetically attached to the metal framing that goes around. So it's all sealed in that hood, which is always continuously vented by an explosion-proof fan. There are vents in the bottom that draws in air from the bottom of the building and through that hood area. And the idea is that if there's any hydrogen leak, it's immediately vented. We have hydrogen sensors in the lab. We have hydrogen sensors in the hood. Whenever the hydrogen concentration gets to half of the lower combustion limit, which is 4%, so when it gets to 2%, we would shut down. We have an air movement sensor in the hood. Whenever the ventilation fails, we would shut down. And that's trying to be as safe as possible. We have taken hydrogen from the electrolyzer, in fact we do this frequently, and dumped it straight in the hood. And with the fan on, it barely budges the needle on the hydrogen sensor. And what that's saying is, and this gets back to the comment somebody made earlier, that hydrogen is so buoyant and so diffusive that it doesn't build up at all. And even if we turn the fan off, it is not possible to get a combustible mixture inside the hood. That is, the natural buoyancy of hydrogen going up the duct is enough to carry it up and away before it reaches a combustible mixture. And what else is in there? We have a small battery. I'll talk about that in a minute. We have a chiller which sends chilled water to condensers. We condense the water, as much water out of the gases as we can before we put them in our storage tank. So we don't end up with a small lake inside the storage tank. Okay, next slide, please.
You're bringing in outside air, Peter, so it's full of salt and stuff, right?
Well, yeah. It remains to be seen how long the fan lasts before it falls apart and things like that. Which is an issue. Stainless steel corrodes in this environment.
Fans are easy to replace, but
Yeah.
all this other stuff.
Well, so far we haven't seen much corrosion, so I'm fairly hopeful. The air does come in from under the building, so the airborne salt, the stuff, the spray that gets thrown around in a big storm or something like that, that is less likely to make it into that airstream just because it's got a very convoluted path. But, it remains to be seen how corrosive this will be. This is a close-up of the electrolysis module. It is, that warning high voltage sign is something I got to change to warning low voltage one of these days because it is low voltage. You can grab it like this and nothing happens when it's on. That is a stainless steel end plate. There's another stainless steel end plate. And there are 12, this is a 12-cell module. The reason we chose 12 cells is somewhat of a long story, but the short part of it is each cell operates at about 2 volts. So if you have 12 cells in series, you end up with a 24-volt electrolyzer. It is possible to put many more cells in series. And Teledyne, who makes this electrolyzer, sells a module which is very similar, which has 120 cells in it. So that would operate at about 240 volts. And of course, you could gang them up in series so that they operate at even a higher voltage. Okay, next slide.
What was the cost of that unit?
$36,000. $6,000 per kilowatt. It's about a 6 kilowatt electrolyzer. But having said that, in a much larger size, the cost, even today, when electrolysis is still a specialty kind of, electrolysis equipment is specialty kind of equipment, you can get the price down to about $1,000 a kilowatt, so about 1/6 of this. And if this became a technology which was utilized to a large extent in this country, the price would come down. The materials cost is not that great. You're really paying for engineering in this device. I might say that having paid for the engineering, we had to do a lot of re-engineering and redesign of this system to work with a photovoltaic system. Yeah.
One question about the electrolysis. I've tried this at home with copper electrodes, but I get hydrogen, but the oxygen always corrodes the electrode. So how do you capture the oxygen?
Well, these are special electrodes which have been developed over many years and are carefully done so that they don't corrode. Also, we use deionized water and purified electrolyte. It's potassium hydroxide is the electrolyte. And as a result, they last a lot longer. They don't last forever. There is maintenance required, and eventually you've got to throw the module out and start again. But different materials work better. These use stainless steel electrodes, and which are alloyed with nickel and plated with stuff that Teledyne won't tell me.
When hydrogen is exposed to air, does it recombine with the oxygen in the air?
Well, generally not, unless there's a catalyst present or some initiator, like a match. You can take hydrogen and oxygen, and even though thermodynamically, certainly there is a tendency to form water with a bang, you can take hydrogen and oxygen and mix them in combustible mixtures, in stoichiometric mixtures, exactly the right amount of each one, and they'll sit there for millions of years. The kinetics are very slow. The reaction is extremely slow unless it's catalyzed or it's initiated. But once it's initiated, it's an explosion. Yeah.
Is there any reason that, seems how the thing's pretty expensive in the first place, you couldn't gold plate? I don't think gold reacts with any of these things.
Well, the question is not just durability, it's reactivity too. That is, you want a couple of things to happen. You want this to last, but you want it to work well at a fairly low voltage. And those things don't necessarily, those properties don't necessarily go together. So it's a compromise.
I might just add that I've operated electrolyzers since the mid-1960s on steel electrodes, unplated mild steel electrodes. But the key is, as you suggest, using an electrolyte that doesn't attack the electrodes. You can run steel electrodes within potassium hydroxide very successfully, so long as you don't poison the system by adding solid precipitates or dissolved precipitates in the water that foul those electrodes. In other words, keep fluorine out and they'll last a long time.
Yeah.
Is there any technical reason why you can't build that out of plastic?
Well, I don't know is the answer. It would have to be a conductive plastic. And actually, that's a good question.
Aren't you really though just dealing strictly with the electrodes, and the plastic would simply be the container?
Well, these already have, the electrodes are metal, but the frames are plastic already.
Yeah.
So
The outer frames that hold this thing.
You could build out of plastic without any limitations of it.
What's that? I didn't hear.
You could build the containment vessel out of plastic.
Yeah, although the end plates have to be conductive. I mean, here, actually show the next slide, please, John. Here's a side view of the module. These are the end plates, and these are the wires. So the current goes in here, through there, and out here. And it's got to be conductive.
Well, why would the end plates have to be conductive if the current path is strictly through the electrode?
Well, I mean, you got to get, here's our power. It's coming in two big wires. And you got to get it into the electrolysis module and then back out again. How do you do that? Well, the easiest way to do that is to have a metal connector and bolt it onto a metal plate.
Right, but what I mean is, if the end plates were plastic, you could always bring a stud out and still make.
Sure.
Okay.
That would work. It's just that at $36,000, they can afford stainless steel end plates.
But I'm thinking maybe. Okay.
Well, the conductive polymer may not be cheaper than the stainless
Yeah.
steel, but
There are,
what works the best is what he's getting at.
but for both fuel cells and electrolyzers, conductive plastics will fulfill an important need, I think, in the future. And I'm not sure how that's going to happen, but I think it's got to happen in order to get the price down to a reasonable level. Yeah.
Does it make any difference, the configuration of the anode, whether a flat surface is less efficient than a round or a pointed or a square or whatever?
Why do they make that round, you mean?
No, I said, which is the best? Is the
I don't
flat surface
think-
any better, more efficiently, or is the surface with many angles and many sharp edges better than others?
I really don't think there would be a difference. I mean, the current goes this way, goes through here, and across the kind of geometry you have really is immaterial. It's just easier to make things round, and it's compact and easy to machine and things like that.
Most ionization takes place at a point better than at a flat surface. That's why I wondered, maybe different.
Oh, I see what you're saying. Yeah, but you've got to have a large flat surface to get this current through at a reasonable current density. So the bulk of the surface has got to be a large flat area in order to have a lot of area to get the current through and generate the gases. And there's no way around that. Otherwise you'd have too high a current density. And you start burning things up and burning holes in the membranes.
Have they tried cold field emission on any of this stuff yet?
Say that again?
Have they tried cold field emission on any of this stuff
Cold
yet?
field emission, I don't know what
They
that
use
is.
X-ray generation. I mean, they just
I
have
don't know.
all the through the points, and you don't need any heat in there in order to get ionization to take place.
What? I don't know.
Let's let Peter move along a little bit now so he can explain his whole system, and then we'll have more time for questions.
Yeah.
Given voltage and current, would the area of the electrode determine the rate of hydrogen production?
Yes, exactly. Yeah, that's true. Okay, next slide, please. This is our control system. We have two, this whole system is run with a Macintosh SE microcomputer. And this is Ron Reed, by the way, sitting at the computer. The computer on the right is the control computer, and we wrote all the software. Tom Herron did most of the work, wrote all the software which controls this system. And what the computer takes input from the environmental inputs from the system, how much current is coming from each of the arrays, what's the temperature of the electrolyzer, what's the current, what's the pressure in the tanks, etc. Lots of different inputs, and then makes control decisions based on that information. The computer on the left is a monitoring computer. This is an experimental setup. We're trying to optimize operation and take data, and that computer records about 30 pieces of information. Temperatures, pressures, currents, voltages, etc. And from that, we're able to analyze how things are working. All right, next slide, please. This is the electrical switching gear. These are the disconnects for the array and the inverter and the battery and the fuel cell. This is the disconnect for the electrolyzer, 400 amp disconnect. And those are the diodes up above that big can. This big can here houses all the other switchgear, mostly relays and diagnostic equipment. I think I have a picture of the inside of that. Yeah, there's the inside of the can, and those are all the relays and buses that distribute the current one way or another. I should say that we have done our best. I think John Wiles is here. Is John Wiles here? Anyone?
He's out of class.
Yeah. John Wiles helped us with our wiring. We have done our best to try to follow the National Electric Code in wiring this system. It has been a struggle. And John helped us to a certain extent, and to a certain extent we just had to use our imagination because the code is still being developed. But all these disconnects and all the wiring is set up to conform to National Electric Code standards. And as a demonstration project, I think it's important that that be true. The safety standards, there are no international safety standards for hydrogen energy systems at this time. There's an effort underway in Europe in the what's it called? The International Standards Organization? What's that called? ISO. Yeah.
ISO 9000.
International Standards Organization. To write safety code for hydrogen systems. But that hasn't happened yet. And what we need is a John Waddles in the hydrogen field. You know, write those kinds of regulations. Okay, next slide, please. This is some of our gas measuring equipment. It's also inside a box which is vented. You can see the vent pipe up here. And what we've done is all the fittings for hydrogen are either outside or in this vented enclosure and in the hood. And that's our effort to make sure we don't have a hydrogen leak inside our laboratory building. And this is gas measuring equipment, both electronic and visual. This is pressure measuring equipment and a solenoid to shut things off in case of a safety shutdown. The solenoid connects the tanks to the building, and in case there's a safety shutdown, the solenoid would close and not allow gas to come into the building. The tanks are outfitted with so-called excess flow valves as well, which means if there's any catastrophic leak downstream of the tanks, the valve slams shut and the leak would be stopped. Okay, next slide, please. And here's the system in action. This is the only thing that moves in the whole system. And in fact, when we first, these are bubblers. The bubbles on the left are hydrogen bubbles. The bubbles on the right are oxygen bubbles. And otherwise you couldn't tell them apart. The hydrogen bubbles are bigger. Before when we first built this system, we didn't have bubblers. The bubblers have served three useful purposes. One is they give us a visual indication of flow, which is real useful. Two, they wash the gases, because the gases have come out of a potassium hydroxide reservoir, and as a result, they have potassium hydroxide, a little bit in them as an aerosol. And these bubblers wash that, especially on the oxygen side, they wash the gas and take the potassium hydroxide out. And the third, and probably the most important purpose, is they allow something to move and people have something to look at when they look at our system. This was a suggestion of Hartmut Stabe, who is a German who is in charge of the only other solar hydrogen facility in the world, which is in Stuttgart. And he said, you need something for people to take pictures of when they come.
Have they resolved the problem with the hydrogen ion collecting itself on the anode? Is that any problem anymore? Have they solved that?
Well, that isn't a problem for us.
Well, there have been in the past, made imitation operation. It's gone into the pipe. If you had to pipe the hydrogen ion to get any oxygen out and so forth.
Let me say a word about safety. Somebody asked originally. We have both hydrogen and oxygen in this system. So far, it's been my experience that the hydrogen is much easier to deal with than the oxygen. We've chosen to collect the oxygen. This system was not designed, the electrolyzer was not designed to collect the oxygen originally. We have redesigned it so it can, and the oxygen has been more troublesome than the hydrogen. Pure oxygen makes anything into a combustible mixture, anything that will burn into a combustible mixture, and therefore is particularly dangerous. The hydrogen, if you keep it away from air and oxygen, which is not that hard to do, is fairly easy to deal with. And I hope we continue to be a safe operation, but thus far we have been, and the hydrogen, at least from my point of view so far, is relatively safe and easy to deal with. Yeah.
Have you considered odorizing the gases?
Well, we haven't done, no, is the answer, but it could easily be done. I mean, for our system, we're not in a situation where we're delivering it to a home or something like that, and we have these sensors in the lab and in the hood, and they're much better than our nose, and they're, not only are they much better, but they're hooked to the computer, so that there's an instantaneous response to shut the system down as soon as there's any kind of combustible mixture. Yeah?
How does the hydrogen determine which way to go in the oxygen one way?
Oh, well, the frames in the electrolyzer are set. The hydrogen comes off on one side of the membrane and the oxygen on the other side. And the frames are set up with manifolds and holes to deliver it one way or another. So it just does what it does, and you have to design the system so that it comes out the right hole. Yeah.
Is asbestos really the only known material for the memory?
Well, it is in this module, but no, it's not the only known material. There are other kinds of electrolyzers, but this electrolyzer uses asbestos for the membrane. Although I might say that, you know, asbestos has got a bad name, but it's used as a membrane here. It's pretty safe. First of all, it's wet. Second of all, it's inside the module, so there's no way it's going to become part of the environment. Yeah.
What's your peak production throttle on the electrolyzer?
This electrolyzer puts out, and the best we've ever seen is about 25 standard liters a minute. So that in a day of operation, just to give you an idea of what the scale is like, in a day of good operation of this system, we produce about a gallon of gasoline equivalent. That's it for the equipment that you see.
What would it be in cubic feet, roughly?
Well, it's about 1.2 cubic meters a day. So,
30.
huh?
30.
Yeah. Now, oh, that's pressurized though. That's at 100 psi.
Yeah, it
So
comes out
multiply
about
by
100.
7.
Self-pressurizing about 100 times?
Yeah, that's right. Yeah.
Is there an ideal cell voltage you should shoot for?
Well, this is not the best electrolyzer in the world. The Germans have built one that works a lot better. This has a cell voltage of about 2 volts per cell, as I said. The Germans have gotten down to 1.65 volts per cell, which is a lot better, obviously. Although theirs is a tweaked up, not commercial kind of module. I think eventually, probably about 1.8 is a reasonable cell voltage for a commercial electrolyzer. I don't think it'll be worth the extra trouble and expense to get it down much below that. Yeah.
Why run low electrolyzer voltages? Why not have a higher voltage electrolyzer with more space between the electrodes and do it that way?
Because then you need more power. The power is the voltage times the current, and what you've got to do is configure. You're using more power and you're producing more heat and less hydrogen for the same amount of power.
Actually, it's just heating the fluid in between.
That's exactly right. Yeah.
I'm having trouble with the bottom line on this. It's going to take 100 years to amortize that one part of the machinery, at a gallon worth of gas.
Hey, yeah, that's true. You're absolutely right. This is a prototype system. This is way, way more expensive. I mean, people hit me over the head with that all the time. And they're right. You know, I just have to sit here and take the blows. But if the next stage, the next step in the development of this technology is building a pilot-sized project. And a pilot-sized project, I think that today, if we set out to do it in Arizona, say, for example, and you know, someday I hope to do that, that we could demonstrate right now that we could make hydrogen for about $10 a gallon, right now, with this technology. And that as soon as it gets larger, it gets from, pilot size, I'm thinking maybe 50 or 100 times as large as this. But then when you're talking about supplying Los Angeles with, or Phoenix with gasoline, with hydrogen instead of gasoline, you're talking about a much, much larger system. And when you're talking about a much, much larger system, the economies of scale really start to play in. And then the cost will come down.
Is that $10 a gasoline gallon equivalent?
Yes, that's what I'm saying.
How
Yeah.
far does the hydrogen go?
What do you mean, how?
Gallons of hydrogen do with it versus the
Roy?
gasoline?
You can usually improve the thermal efficiency of a heat engine on hydrogen. And you might think of making about 1.5 times the fuel economy with hydrogen as you do with gasoline on a BTU analysis or a calorie analysis.
That's based on an engine.
That's based on a heat engine.
And there's more. There are other savings. We don't build our cars very efficiently, not only the engine, but the rest of the car as well. I mean, we could reduce the drag on the car, reduce the weight. All that will increase the fuel efficiency. Yeah.
I'm just curious what, like, when you buy tanked commercial hydrogen, what does that come out to? I mean, what are they producing commercial hydrogen?
I don't know. Anybody know?
$7.50 for 100 cubic feet, $7.50.
$7.50 for 100 cubic feet. So,
They get it through hydrocracking though, rather than
Yeah.
producing it through. It's a
So
waste
to-
product of the oil industry. So.
Yeah. It depends, in that instance, on the cost of the hydrocarbon that you're using. If you're using natural gas, it may be less expensive than gasoline because natural gas is used as a source of hydrogen for extending the use of oil in the manufacture of gasoline. So it's quite economical if you have very large scale and can extend the use of oil in making gasoline with hydrogen to select natural gas as the feedstock.
One question.
yeah.
The biggest problem if you're making hydrogen is your electricity source.
Yeah.
Could you use more panels to get more hydrogen? Or-
Sure.
Or more efficient
More panels
cells?
cost more money.
Yeah, exactly. But I'm saying if you had a more efficient cell, you would have more hydrogen.
Sure. It's, yeah, gotcha.
Well, your drawback is the amount of power coming out of the cell.
Well, that's not the only drawback. That's not the only drawback. Yeah.
Is your system continuing to evolve?
Oh, sure, yeah, it is. And I'll say a word about that.
What are your next steps?
Yeah, I gotta get going, we're running out of time. Here, next slide, please. Okay, this is, let me go through this quickly. This is the basic logic that we use, and this is what the computers do. We ask, is PV power available? If it is, we run the load with the array. If there's extra power available, we run the electrolyzer and store hydrogen and oxygen. If there isn't PV power available, we ask whether there's hydrogen and oxygen available. If so, we run the load with the fuel cell. If not, we return the load to utility power. A typical standalone system. Somebody probably is thinking, why don't you use a battery instead of this hydrogen system? That's a good question, and the fact of the matter is that a battery type system would work much more economically than this system would at the present time. But our goal is not just standalone power. Our goal is to develop this solar hydrogen technology, and as a result, we're doing it this way. Next slide. And this is what our computer looks like when we're running. And I wish I had more time, but let me go through it quickly. These are the 12 subarrays. And this is a typical moment in operation. The current from each subarray is right here. So we're getting about 20 amps from each subarray. This is a sunny period. It's the middle of a sunny day. And right now, 2 of the subarrays, these first 2 are running the load, which gets 35.5 amps, way more current than it needs. The extra current charges the small battery, which is charging with 15 amps and is now at about 30 volts. As soon as it gets to 31 volts, it would be fully charged, and we would take one of these subarrays and switch it back to the electrolyzer and then run the load with only one subarray. Meanwhile, all the rest of the current is going to the electrolyzer, 209 amps, and that's making hydrogen. It has an emergency shutdown switch. We also, let me just say a word about the electrolyzer. The electrolyzer current has to be limited when the electrolyzer is cold. That's not something that you normally have to worry about in electrolysis, but you do with PV electrolysis. And in the morning when the electrolyzer is cold, right now the electrolyzer is at 61 degrees. That's warmed up. So we can give it a maximum amount of current, which is 275 amps. That's this here. But in the morning when it's cold, the most we can give it is about 125 amps. And then because too high current, when the mobility of the electrolyte is reduced, will damage the membranes. So as the electrolyzer gets warmer, we can give it more and more current, and we keep track of that. Right now it's warmed up, so we can give it maximum current. Okay, next slide, please. Here is the kind of efficiency that we get in this system, and I'll say some words about that. The hydrogen, the electrolyzer efficiency, the voltage or the hydrogen produced compared to the electrical energy put into the electrolyzer is about 69%. That is not bad. It's not quite as good as the German electrolyzer. By the way, when you see theoretical studies done, people often quote electrolyzer efficiencies of 80 or 90%. In real life, you get 70%. The hydrogen, I'll just talk about the hydrogen efficiency. The hydrogen efficiency is 5.7%. That's based on the entire array, because we have no way of knowing how many of the subarrays are connected to the electrolyzer and how many to the load at any one time. For a stable period of operation, we have measured the actual electrical energy produced from the sun to hydrogen efficiency of 6.8%. That is the overall system efficiency. That's a world record. This is the best that anybody does. The Germans are about 6% at best. So this is about what you can expect from a system. About 6.87%, I would say. That is sunlight to hydrogen. And that's what you're looking at. So if you're thinking of driving the U.S. economy, that's the kind of number that you can plug in for producing hydrogen energy from the sun.
That's approximately the product of the PV efficiency and the electrolyzer.
Approximately.
That's sunlight at our sea level here?
It doesn't matter. Doesn't matter.
Current technology.
Current technology, yeah.
But that's only using PVs, no? That's not any other alternative source?
That's PVs and electrolysis.
What was the efficiency of the electrolysis of electricity for hydrogen?
That's on the bottom there.
So you have some kind of calorimeter or pyrometer?
Yeah, we have a pyrometer. We have two pyrometers that measure the sun all the time.
And this is at fairly high insulation values?
Yes. Yeah, that's right.
But you have obtained 90% efficiency from your electrolyzer. I was there one day.
Yes. At very low currents, when the electrolyzer is heated up, under certain conditions you get much higher efficiency. But this is the bottom line. This is what happens over a long period of time when you're warming up, cooling down, shutting down, switching. All those things cut into the efficiency, and that's the bottom line.
What is the approximate liquid volume of the electrolyzer?
About a gallon. About a gallon of electrolyte. Let me say a word about the fuel cell. Go ahead.
When you measure efficiency, you're talking about the higher heating value or the lower heating
Yeah,
value?
higher heating value. That's right. That's exactly right. We don't have a fuel cell. We've been trying for 2.5 years to get a fuel cell from the world, and the world has not yet responded. We need a certain kind of fuel cell, a proton exchange membrane fuel cell, which has certain properties. It will operate at a low temperature, and it will turn on instantly when we need it to. That is, when we need to switch from PV power to standby power to hydrogen generate electricity, we need to do it right now. We turn a switch and the power has to be on. Most commercial fuel cells are of a type which have to heat up and cool down and can't deliver power that quickly. That's the kind of fuel cell, the kind that we need, the proton exchange membrane fuel cell, is the kind that will run in an automobile someday. And because we have been unable to get one, we have recently started our own project to make our own. And hopefully, if I come back here next year, I can tell you we have a fuel cell that works. That would be nice.
Can't you heat it with an outside source? Couldn't you heat warm with an outside source?
Yeah, but the parasitic power would be tremendous. That is, you waste a lot of power doing that. We're trying to be efficient here.
What temperatures are we talking?
Well, 200 degrees C typically, or depending on the technology, 650 degrees C.
What temperature does the electrolyzer operate at?
About 60 to 70
Degrees C.
degrees C. Right. Yeah. Thank you very much.
Peter, as a lead into what Roy's going to say, what's the efficiency of your PV modules?
The modules are about, well, you see the PV efficiency here. That's actual measured total array efficiency. The module efficiency is about 12%.
Chevron Research and Technology in Richmond, California. And my job puts me in contact with a lot of things that are going on in hydrogen. Part of my job description is to follow emerging hydrogen technologies and input information on what's happening into our Technology Awareness Committee. We're not currently involved to a great extent in solar hydrogen, but we're about as involved in hydrogen as any company in the planet can get. And I believe that at the moment we're the largest hydrogen producer in the world. We don't sell it, we use what we produce, and almost all of it's produced from natural gas, which is reformed with steam to make hydrogen for upgrading gasoline and diesel fuel and other liquid fuels that are in current use. And in Richmond, for example, we have a hydrogen plant that is a utility and is used for reforming gasoline, diesel fuel, purifying products, upgrading lubricating oil stocks. Some plants, they use it for manufacturing of fertilizer, like ammonia. But basically, we take natural gas, which is mostly methane, and reform it to make the hydrogen. The byproduct is carbon dioxide, which is sent over to another plant where it's made into dry ice. And this is pretty typical for the petroleum industry to do this. And most of the merchant hydrogen that's available for the electronics industry and for sale to the public, for gas welding and this sort of thing, is made through other processes or on a smaller scale. Another big hydrogen production sink, if you will, is the space program, and most of the rocket engines run on hydrogen and oxygen. So there's a lot of this that's available in the commercial world already. It's just that it isn't made by a solar process. It's made from starting material, which is a fossil fuel or a biological byproduct. The picture that I have on the board here in the back, I'd like to start with and end with, and I've used it because it's a graphic and I thought that it might spark someone's imagination. In the job that I'm in, I have a lot of time to think about things, and I also have a lot of work to get out on a given day. So one of the things that I like to do is dream a little bit. And right now, if you look at what's available commercially for someone that's sitting in this audience who might want to get involved with hydrogen, you have a fine research kind of a tool like Peter Lehman just described to you, where it's computerized, has instruments on everything, and allows you to tell really very well what's going on in the total system so that you can study the economics, you can study the components. And I think when you leave here to see the other end of the scale of what can be done with photovoltaic electrolysis, you might like to go and see David Booth's display, because he is perhaps a little modest when he says he's a student. He's also a teacher. And he teaches at the Solar Energy Research Institute. He has some courses this summer on solar hydrogen. But he's got a demonstration of what a person, any one of you, could do if you put your mind to it. He's taken photovoltaic cells, I think he has about 4 on the display outside, and he's hooked them up to 4 electrolyzer cells that are this big around and this long. They're $125 a piece. And they run at the magic 1.65 volts. They're every bit as good as the ones in the German laboratories. They're made by a guy in Lineville, Iowa in his barn. And for $125, you can be in the solar hydrogen business with 1 PV panel. So take a look at David's show over there, and I think you'll find it fascinating. Well, what I'm going to take you through here is what I call my dream. Sometimes dreams have happy endings and sometimes they don't. This is a dream that started in 1979 when I was working the photovoltaic group at our lab. And I came across some work that had been done by the French over in Nancy, France, that was on thermolysis. Thermolysis is shown up here as one of the branches off thermal energy, where you take solar energy and you take the heat and light and use it to do a process which is called thermolysis. And in the picture that's up on the board is an overview of how we viewed the possibility of doing thermolysis in 1979. And basically what it consists of is a solar concentrator. It would be a mirror, preferably, probably a parabolic dish, something that looks a lot like a satellite receiver, only has a mirrored surface. And that would focus sunlight by following the sun as it goes through the sky during the course of the day, and concentrate it onto one very intense hot spot where you have a much higher quality heat than you have when the sunlight falls on a diffuse surface like you find in a solar water heater, for example. There are some solar concentrators around here at the fair, and you've probably seen them. There's some parabolic dishes, there's some cylindrical concentrators. There are also some lens concentrators like Fresnel lenses, plastic lenses you might have seen. The idea here, there's a little better shot on the bottom. If I get it up high enough, you can see it. Is the sunlight would come in and primarily in direct beam parallel rays, reach the mirror on the back, and get focused into a focal point. And we went looking for a large mirror so that we could start out doing some work for this. We ended up with a searchlight. We picked up for about $500. Used to be used for advertising openings of car lots. And that became our concentrator. It's a 5-foot dish, and it's a really high-quality mirror. Well, inside the searchlight, we installed a reactor which originally was conceived to look something like this, and it would have a transparent window in the front that would allow the sunlight that's being concentrated to come in. It would have a target on the inside which could reach a very high temperature, and then we would have a water vapor feed which would come around the sides and pick up the waste heat and be introduced so that it would flow over this very hot target. And downstream from the target there would be an attempt to separate any products that were formed when the water was heated to its decomposition temperature. This is what happens when you heat up water to high temperatures. Let me see if I can get that up so that you can see it a little better. What we're looking at is a temperature scale on the bottom. This happens to be in degrees Kelvin. If you like degrees centigrade, just subtract 273 from that. On the left-hand side is a log scale of the mole fraction of the particular element. And you can see that there's a family of curves here. The one that's coming up and off here on the bottom is the oxygen. And the one that's up above that that's kind of going off the screen is hydrogen. Just bring that down so you can see. So in the beginning, if you start out at a very low temperature, you've got completely water. There is no hydrogen and no oxygen. It's just a water. It's the starting material. But you can see that as you increase the temperature and you get up in the neighborhood of 2,000 or 1,800 degrees, something starts to happen. And what's happening is the water is starting to decompose. And this is an equilibrium diagram. And I'll show you a few reactions that go on here on the next few graphs. But basically you can see that the water goes away, and by the time that you've reached about 3,200 degrees, there is no more water left. It's all broken down into the components of H2O, 2 parts of hydrogen, 1 part of oxygen. That's why the hydrogen curve is up higher. The reason it isn't twice as high, again, it's a log scale. Down here you see a couple of other curves. First of all, this one, which is the H2 curve, and this one is the O2 curve. And there's an OH curve in between. And these are all possible products when you decompose water. The OH curve, sometimes called hydroxyl. And the H2 and the O2 are the diatomic gases. If you go buy a bottle at the merchant supply of hydrogen, you'll find that it contains H2. It's not H1. H1 is called atomic hydrogen. And if you get up to a high enough temperature, you see that H2 going away and the atomic hydrogen growing. And when you get up to 3,500 degrees or so, it's all atomic hydrogen and atomic oxygen. There's so much energy that it can't stay together in a diatomic molecule any longer. So what we're trying to do is operate where the dotted line is. This is around 3250 Kelvin at this pressure. And we've been able to operate there successfully. That may sound like that's great, but that isn't even half the problem. The real problem is separating them before they recombine. Because this hot spot is very small and the gases are flowing through it, and they're only at this temperature for an instant. And as soon as the temperature falls, when it leaves the hot spot, it goes right back to water. And you've got to stop that back reaction if you want to get any of the hydrogen.
Well,
Yeah.
what kind of materials do you use to contain something at 3200?
We're using zirconium quartz. Zirconia is zirconium oxide. It's a ceramic. And there's enough of a temperature gradient across the surface that even though these temperatures are higher than the melting point of the zirconia itself, it doesn't melt because it's got a gradient through it. And the quartz
And it conducts the heat away fast enough.
conducts it fast enough away into the other side where the cool fluid's coming in that you can make it survive. There's a surface film across there that acts like a further gradient that's in the gas phase. These are the reactions that are important. The one up on top is the one that most people see where the water goes to hydrogen and a half oxygen, number one. But there's also some other reactions where the hydrogen decomposes from diatomic hydrogen into atomic hydrogen, likewise for the oxygen. And once you have atomic hydrogen and oxygen, you can form the radical, or the grouping OH. Each one of these has a pressure equilibrium constant associated with it, how much energy it takes to make that reaction go. So you can put these together, and that's how these curves are derived. Well, after I saw the French work about decomposition of water, I looked into their methodology, and this is one of the types of work that was done by Guillermo and Lede back in the early 70s. This is about 74 to maybe as late as 1981 or 82 that they're working in this area. Basically what they would do is they put water into the center of a spherical globe so that the interior of the globe contained water vapor and had a surface, and then they used a parabolic mirror to concentrate the sunlight up onto this globe, and then they would remove the products of hydrogen and oxygen through these tubular membranes. And they in that work achieved efficiencies initially of about 1% conversion, where they were able to capture about 1% of the hydrogen that was produced. And then later on they had a few pieces of data where they used a more elaborate quenching scheme, putting cold argon on it, where they obtained about 5 or 6% conversion. This is another geometry for the same type of separator. This one was to use a linear concentrator, a cylindrical type of concentrator with tubes that ran down the focal point like a line focus type of geometry. All the funding was cut off by the French government in the late 70s after the first fuel crises were over. So I went over and had a chance to talk to the people, and we were mostly concerned that the reason that thermolysis had never come to any commercial success was the fact that no one had ever developed a separation method which could quench these products quickly enough to prevent them from going back together again. So this was the concept that we put together for our first solar reactor, and it has elements of a whole system included here. This is actually below here, can be ignored because it's external to the actual system we were working with. The solar heat would come in and would go through a photodissociator section, which would cause the reactions that you saw in those curves to occur. And then we were going to try to use a separatory nozzle to separate the hydrogen oxygen. And this technology comes from the nuclear industry. It was developed by a person named Becker in Germany. In 1955 was the first paper published on it. And it was used to separate uranium isotopes for purification of uranium. And so we thought that it might be applied here, and that was the beginning of this project. So our first reactor used the solar heat source, which is a searchlight, and we installed our reactor at the focal point of the searchlight. Here's the representation of the mirror, and the focal point of this mirror is very close in. It's not like a lot of mirrors where the focal point would be way out here, but this one has a relatively low F number. It's about 0.6. So it would come in the window and it would focus on a target, which we call the photodissociator. And then back in the section behind here is the separator. And we had two product lines, one that would be dealing with a light product containing hydrogen, and one that would be with a heavy product that contained the oxygen. Both of them were expected to also contain water vapor, which went through and wasn't converted. Then this goes to an analysis system. Here's your feed water in blue. You can see how it comes up the outside and goes into the nozzle. And then the red is the hydrogen and the green is the oxygen. And there's also an analysis system. Initially we were using a gas chromatograph to analyze the gases. We're now using a residual gas analyzer.
Could you go into the principle of the nozzle a little more?
Yes. This is probably the best one I have to go into the nozzle. This is called a photoseparatory nozzle. We have a patent on it. The group of people I might acknowledge who've been working with me on this are Ronaldo Cortez from Shadowbox Construction Company and James Healy from Healy Construction Company, Mark Hayes from Illumination Computer Services, and myself in conjunction with support from HI Solar Company. The nozzle arrangement is that you have two components. Let me start from the bottom and then I'll work my way up. The photodissociator would be in this area up in the front, and you would have heat falling on this surface. This surface actually has been eliminated, and this surface, so that what you have here is zirconia-coated Delaval nozzle, where you have a pressure ratio across the nozzle that causes flow through it. And the surface of the nozzle is running white hot. Now, we've measured the temperature of the surface using an optical pyrometer, and we've seen within the measurement error 3250 Kelvin. And we think that we're within 50 degrees of reading it accurately. So you have dissociated gases arriving at this point and expanding into an area that's at a lower pressure. And the diagram that I have just above this, at about 1 millimeter downstream in the flow field, shows a dotted line, which is the light gas, and a heavy line, which is the heavier gas. And you can see that the two spatially are not equally dense in the density profile. And transverse diffusion is thought to be behind this. That, in other words, the light gas tends to diffuse this way more than that way. And the heavier gas, through inertia, tends to propagate in the direction it leaves the jet. Yes.
Is that sonic flow through there?
It is, it's choked at the throat. So we run a critical pressure ratio across it to keep sonic flow there. And it makes a shock wave.
Is that critical process?
I believe it's critical that it wouldn't work without the shock wave because the shock wave forms an envelope of density gradients very sharp across the shock wave. We'd like to be able to visualize this. We've got some optical components in there to try and put a beam of light through there and be able to visualize the shock wave.
Have you done any computer modeling?
We've got a model, but it isn't in the computer program, no.
What about rifling the nozzle and using centrifugal force to fling the heavier gases out and taking the hydrogen out the center?
It's interesting you should say that. There's a patent that has been issued for a centrifugal separation device based on a tungsten spiral that would be machined out of tungsten. And I called up the guy who had the patent, and he said he'd never made one, but he'd like to someday. So, yeah, it seemed like a good idea to me, but I don't know anyone that's ever tried it. There is such a thing as a gas centrifuge. Pardon?
I was wondering how you got a patent without actually making it.
Oh, it's quite common to grant patents without any working prototype.
All you have to do is draw a good drawing.
If you can convince the examiner that it's unique, you can get a patent on it.
Useful.
So the final part of this is that out in the flow field at some distance, in this case we're talking about 3-4 millimeters downstream from a nozzle that's about 1 millimeter at the opening, you have what's called a beam skimmer. And this is nothing more than a tube that comes down to a converging cone and it has a very sharp edge that goes all the way around. The one here is round in geometry. I'll show you some pictures of these parts in a moment. This is all made on a fairly small scale because it had to be scaled to our searchlight. So we didn't have any 30-foot or 1,000-foot mirrors out in the desert or anything. One thing I discovered early in the game about this is that small is beautiful and big is not required. This thing could be made big enough to hold in your hand and it would still work, or it could be as big as a football field, so it's scalable. The separation factor is something that we really care a lot about, and what this is the ratio of how much of one gas you have to how much the other gas you have in the sample that you pull through here or the sample that you pull out on the periphery. And you want to have the biggest separation factor you can. If you could get 100% separation factor, well then you would have all the hydrogen and all the oxygen separate. Right now we're working with pretty low separation factors.
Is that a product in the numerator and denominator?
I'm sorry?
Is that you?
It's a product, yeah.
It's a product.
Mole percentages of each gas. It's just a defined property of a separation that is one that's used throughout the separations industry as a way people can relate their processes.
So what you're trying to do is pull off as much oxygen as possible, and the oxygen you don't pull off will recombine with the hydrogen, and then the excess hydrogen, then you can trap that.
Right. I mean, it's going to recombine and you're going to get water, and you can condense it out at either stream.
Right, but then, yeah, but what's left over is this excess amount of hydrogen.
Yeah, if you had a perfect separation, each stream would have only oxygen, only hydrogen,
Exactly.
but we're never going to be perfect. And they've made separation factors as high as 20 for uranium isotopes, which have a very small mass difference, like 238 versus 235. So the ratio of the masses is very close to 1. And so in principle, it's possible to get separation factors that are quite high because we've got a mass fraction here that's 16 to 1 for hydrogen and oxygen.
What is your separation factor?
We're down in the neighborhood of a couple percent.
But they had a bigger budget.
Yeah, our budget's all privately financed out of people's pocket after they pay the bills each month.
Walt, does all the, if you're collecting the hydrogen from the outside of the splitter, and it's got some oxygen in it. That's going to recombine into your water. Does it all recombine, or do you end up with some oxygen gas and the hydrogen when you're done?
You end up with some oxygen and hydrogen, and some hydrogen and oxygen. We have to force the recombination for safety reasons.
That's what I was thinking.
I'll
So
go
you
back.
catalyze the recombination so you don't end up with a combustible mixture.
Yeah, let me go back here one step to this view graph. This is the one I showed you a little earlier about the whole system. And at the time we drew this, it was a conceptual diagram, and we had a recombination unit on each leg that would take the hydrogen back to H2 and the oxygen back to O2. Well, it also is a recombination for any hydrogen that's in the oxygen. Any oxygen and hydrogen comes back to water. So we run it through that on the way out of each leg. This is some other geometries that were used by the Germans, by Becker and his co-workers in their uranium separation. This one is a opposed jet nozzle. Here you have the feed gases coming in the side, and they run into each other, and then the heavier and lighter fractions go by the way they turn. The light fraction is less inertia, and it turns easier. The heavier fraction goes up the center. This is another one that's can be used for a linear geometry. You have the feed gas, which would contain hydrogen and oxygen, comes in, and then by turning, you end up with a light fraction and a heavy fraction. This is a knife-edge skimmer that's could be linear, so that you could have it in a trough collector. Okay, I'll show you some pictures of what the system we're using at the moment actually looks like. This is the reactor containment vessel, and it's a piece of aluminum that's been bored out and split, and so you can take it apart in two halves. And on the interior is I guess for a lack of a better description, I call it a thermostat. It has two walls with a vacuum in between, and it's silvered, but it's a thermos bottle that's open at both ends rather than just being open at one end like you normally keep your coffee in. That's made out of quartz, and it'll take the direct beam in the event that there's a steering error and you aim the searchlight in the wrong way, it's not quite on the sun, and the beam's off of the center, it come off and hits this quartz, and it'll take the shock without cracking or breaking. And so far, that's the only thing that I've been able to use which will take it. It'll melt stainless steel. It'll break glass just like that. It'll melt aluminum. So I haven't been able to put anything in there that would take a beam steering error except the quartz that's used on the inside.
What is the collector area?
The collector area?
Yeah.
Well, it's 5 feet in diameter, so it's about 1.8 square meters of area it captures.
I'm kind of thinking of that dissolved state of the oxygen and hydrogen splitting apart, kind of like a plasma state or something. Is the molecular charges of the oxygen and hydrogen such that you can actually maybe use some electrical currents to pull them apart?
It's interesting you should bring that up. You can be my straight man on the next talk, because where we've gone from this, if you simply have a thermolysis, in principle you don't have anything ionized. You don't have enough energy there to kick any electrons off of the hydrogen or the oxygen, so they're still the atomic state, not in an ionized state. And as such, they're neutral, and they can't be steered by an electric or magnetic field. However, we're working with a hybrid process that he shows here, which I'll mention just at the end. We haven't got a long way with this yet, but what we're doing is taking thermal energy with thermolysis and adding an electric field to it for the separation, and also to bring it into the excited state up in the dissociator end. And by putting it in the excited state where it's partially ionized, it changes the cross-section of the gas to absorption of solar radiation. which means you can couple more energy into the vapor, because water vapor is quite transparent, and it has several absorption points in the infrared, but not much in the visible. And by putting it in the excited state, you change its absorption spectrum. So I'll get into that a little bit more in a moment. This is a picture of the reactor disassembled, and this is the main reactor barrel, which you saw a moment ago. And this is the back end of it. That normally this part goes back here. And this is the separator arrangement that consists of a mechanical arrangement to move the nozzle skimmer in and out and from side to side to get it lined up. This is the picture of the front end of the reactor with the window retainer on it. It's the same barrel that you saw before, but now you see that this window is installed. There's a quartz window. It's a flat plate. It's not the best. It'd be better if it was a slightly domed plate, but nevertheless, the flat plate's cheapest. And this has a entry angle on it. I think there's another picture I have that shows a little better. And this is the nozzle tube, which is a piece of quartz that's been coated with a thin film of platinum. And then the very end that's white is the zirconium oxide ceramic. And you can see the hole in the center, which is the center of the nozzle.
Are those machinable ceramics, and then you fire it after that?
It's a ceramic paint with an oil base, and you paint it onto the quartz, and then you fire it in the reactor itself. It turns it into an open pore ceramic coating. We just fire it in the sunlight. We paint it on, we paint several coats on, and then put it in the sun. And it thickens, and all the oil is splashed out, and it just leaves this open pore structure.
Was it erosion a problem in all this?
Erosion? No. We run it 4 or 5 hours at a time, and it's stable.
The feather edges would kill you.
Pardon?
The feather edges would kill you on the separator.
Well, the separator's behind the nozzle on the inside. I'll show you what that looks like. This is the separator unit that sits in the flow field behind the jet coming out of the nozzle. This would be inside of that last tube that you saw. They're like nested. And this goes on the end of a stainless tube. And this is quartz, and it has a coating of platinum on it. And right up at the tip is a knife-edged hole that you can move around into the jet.
How do you form that?
It was formed on a hydrogen-oxygen torch in a lathe out of a piece of quartz tube, and then ground to make the sharp edge on a diamond wheel.
Wow. Must take pretty careful machine.
Well, there's a glass shop in Berkeley that made it for us, and they charge $50 a piece. So here's a photo that shows the reactor installed in the searchlight focus. This is the mirror material here that you see. And originally the searchlight had carbon arcs that were used to make the light. And we took all the carbon arcs off and installed the searchlight on this stage. And these are for moving the reactor in and out of the focus point. And the window is up here facing the mirror. And the separator arrangement's here. And then this is the light product line, and the heavy product line goes off the side here. There's a lot of instrumentation on it for measuring pressures and temperatures and flow rates. That's all the wiring is about. Certainly not necessary for the average working unit once you figure out how to make it work. This is the window in the feed ring, removed from the barrel. There's a window right in here, and this thing that's shaped like a shepherd's hook is where we feed the water vapor in. The water vapor comes in through this switch lock fitting, goes through an insulator, And there's a piece of quartz tubing that brings it through. You can see the quartz tubing sitting here, and this is stainless steel. And stainless steel is drilled with little holes so that feed gas can go through the holes and come out. And then from there it goes into the hot nozzle, the white hot nozzle surface. So you can see these little holes here where the feed gas comes through. And one of the things about our nozzle is when we run this reactor, you can't turn off the feed. We found that out the hard way because one day we were running it and somebody turned the valve off too far. We were trying to run a low feed rate. The water vapor stopped going through the tube and the beam snicked off the stainless steel tube. It's gone. Meltdown. Down at the far end of the reactor, we have this analysis system. And this braided tube coming in on this side is the oxygen product line. And the braided tube coming in this side is the hydrogen product line. And we've got a tap that comes off here, goes through a solenoid valve and down into a chamber. And there's another tap here that goes through a solenoid valve and down in a chamber. And their computer program opens one of the solenoid valves and bleeds in a sample. And then down below, this blue unit and the silver head is a residual gas analyzer. So it gives us the composition of the gas. We can tell how much partial pressure of hydrogen and oxygen and water, nitrogen, whatever is in there. And it tells us if we have leaks so that we're not having a leak go in instead of our desired feed gas. And it also tells us how well we're doing on our separation. By monitoring one side and then the other side, we can calculate a separation factor and see how we're doing. This is an overview of the unit in the searchlight with the separator off. At this particular time, the unit that comes in the back with the oxygen separator is not connected, but you can see it's kind of an overview here how the searchlight is in the mirror and the reactor.
How large is that again?
It's a 5-foot mirror, 5 foot in diameter. And this is a diagram that shows where we are now. The sunlight's coming in the front of the mirror through this window. The fireball sits right here at this nozzle. This is the white cylinder you saw. And then the skimmer is right here. And the skimmer can be moved in and out and from side to side to line this up. And then we take our light and heavy product samples to the analysis system. We have a mass flow meter here for feeding the water in. And we're using what we call a pre-ionizer. It's between this feed ring and the nozzle. And we can jack up the voltage on that and put it into a glow discharge. And the question you asked earlier about whether we could separate things by electric field now becomes possible because, first of all, when the water vapor is coming out of this ring and going down into here, we have this whole thing in this area in glow discharge. And some people say, well, gee, how can you afford to use all that electrical energy? Well, really our answer is that it doesn't take much. When we use a DC discharge, we run it in the dark, it takes about 700 volts to cause a breakdown of water vapor. In the light, it takes about 200 volts to cause a breakdown because there's a lot of free electrons coming off the surface by photoionization because the light's hitting the surface and kicking electrons off the ceramic. And we put them in an electric field that accelerates the electrons away from the surface and more of them come off. And so it doesn't take much of a field to make this happen. And the current requires about 3 or 4 milliamperes. So we're only talking about milliwatts to make the process go. And we run it off a little solar cell. So you don't have to plug that in either. The second thing is we got what we call a post-ionizer, which goes between the nozzle and the skimmer, which we hope is going to have an effect on that separation by being able to take any of the charged species can steer them with electric field. We don't have enough data on that to even know if it's working yet. It's just been installed for a couple months, and we haven't run any controlled tests with it yet. So in conclusion, I'd like to put the first one back on.
Just right here, did you ever kind of say, have you been able to measure that, or is this the next step that you haven't got to yet, or have you done this and got a measurement yet?
A measurement on which?
On the separation enhancement.
Well, we get a couple percent separation factor, and it's not enough for this to be a commercial process.
Can you,
Well, we're far from optimized on it, and we have far from the amount of data we'd like to have on it.
So this is right in the middle of this pretty much.
Yeah, we're at the point where we're starting the data collection phase and fine-tuning our spreadsheets, and we want to publish on it as soon as we've got some good numbers. Yeah.
Do you have any idea what you're expecting the ultimate separation factor to be?
Well, we projected that we could be able to obtain an efficiency of the process which accounts for the efficiency of the dissociation unit and of the separation unit of 40%. And this would put it in the neighborhood of the efficiency of the very best solar cells that are available in the laboratory now and could be available in the next few years. And really that's the competition for this process is photovoltaic system. Because if you can have a good enough photovoltaic system, and the efficiency is equal or better, there's no moving parts there, and there's no requirement for pumping. One of the downsides of this process is you have to provide some pumping energy to pump those things through. And so that's a debit that you have to take off the efficiency in order to do all the accounting properly. And I think the advantage of something like this is that you wouldn't need all the instruments. You could mass produce it like light bulbs. It actually is a lot like a light bulb. It's like a light bulb with a couple of flow lines coming out of it. And the concentrator technology is coming down in cost. So we're still optimistic that there could be something viable here. It's all depending on whether the separation can be done at a high enough efficiency. If we could obtain a separation factor over 20, it might be a commercial process. But we're at least an order of magnitude away from there right now.
Well, are you saying sunlight to hydrogen of 40%?
Yeah.
Wow. That's including optical losses and pumping?
Yeah, that's the
and all that?
radiation losses, which is one of the biggest on the dissociator side, and including pumping energy.
That'd be a pretty...
We're running our pumps off of PV, so.
Yeah, but extra PV, right?
Extra PV. Yeah, it's separate from this. We run PV and run an inverter and run the compressors off of the inverter. So it's all solar, but
Nonetheless, you have to count that in.
you have
as
to
part of
cover
the
that.
efficiency.
And where it really comes in is capital cost. You got to have a capital cost that's compete with PV.
To perfect the separator technology, have you considered heating it electrically, just eliminating the sun end of the thing and just working on the separator?
Yeah, we've considered, but we're purists, I guess.
Okay, I'm just curious, because there's certain times a cloud moves over and you slows down your testing.
Yeah, and a lot of times we're ready to make a run on Saturday and it's a foggy day.
That's right.
Yeah, so we don't make a run that day.
Okay, just curious.
Yeah, we felt though, what the French did is they were using arc lamps as the source of their radiation to run their experiments, and we wanted to use solar spectrum, we wanted to use the real thing, so that's been one of our agreed upon constraints all the way through this, is that we would use the real thing and that was going to be it, and nobody would go away from that. Although there could be some useful things done with the separation of gases on a bench test that didn't use sunlight, I would have to agree. So just in summary, what we've talked about here is that this is a concentrator technology that uses something that would be relatively cheap, like a mirror, to obtain very high quality heat energy on a small area, taking energy which is low quality from a big area and concentrating it to high quality in a small area. feeding water as the feedstock, breaking the water, and then separating the products to provide hydrogen, which would be the energy vector. Something that you could use at night when the sun went down or during the daytime. Thank you.
We have one more panelist coming up too. Roy McAlister from the American Hydrogen Association. Okay, our next speaker is Roy McAlister, who's introduced himself before as the president of the American Hydrogen Association. And essentially, he's going to talk about the other methods of production that were not covered in any detail, such as electrolysis and thermolysis. So he's got quite a bit to cover here, and let him get on with it.
Thank you. Well, first of all, let me mention that I've really enjoyed hearing two pioneers tell you about their work. And I would emphasize that in this recognition, you've been treated to an opportunity that's a rare opportunity. You've heard about the work that really is ice-breaking type of work in demonstrating how to make hydrogen. I would like to pick up your areas of interest from your questions, and so feel free to ask questions. But I would open up by making good the promise to tell you how to make hydrogen for 30 cents a gallon of gasoline equivalent. And the way that you do this is pretty natural. And you have the bonus of having odorized hydrogen. It's an important measure, so you know where it is. The way you make 30 cents a gallon equivalent hydrogen that's odorized is by taking waste material, things that no one wants, garbage and sewage, stover from agricultural processes, and use non-union labor to dissociate these unwanted materials to hydrogen and some other constituents. The non-union labor is microbes, bacteria. And the odorization will be noticeable. You'll be able to know where the hydrogen is. But you'll be doing the public a great service. You'll be getting rid of things that they don't want anyway. And if you pick the microbes and nourish them with lots of waste material and provide them with thermal energy, which they need, and this can be solar energy, they'll do a yeoman's job, produce lots more bacteria, adapt to the conditions, even if you feed them poisons, and get rid of what you don't want while you get 30 cents a gallon equivalent hydrogen. Now it's up to you to find the hydrogen and separate it from whatever else is there and put it in your tank and use it. But surely you'll be doing a very good thing for society as you exercise these options that nature teaches. It's also true that you can select the bacteria for the purpose of making mostly hydrogen and leaving mostly carbon behind. And then you can clean up the carbon with thermal processes and get this product. It's much better than having the carbon go into the atmosphere and become a greenhouse gas in the form of methane or carbon dioxide. And I'll pass this around. And it's processed from waste material. But feel free to shake a few grains and chew them if you like, because by now it's been denatured and cleaned up, and it's an example of what you can use as a building block to make good things out of carbon chemistry. Much better than having it go into the atmosphere as a greenhouse gas and become part of what we have started to realize as the forcing function in changing the weather. Carbon in the atmosphere is changing the weather. I'd like to, if there are no questions on that approach, I'd like to go on to others, but please.
Does anyone have a working system currently?
Well, yes. Every one of us is a working system.
No, that's get rid of that.
Yeah, there are a number of cities that produce methane, and they produce quantities of hydrogen with their methane. They're usually just taken as a fuel value. if you want to produce more hydrogen and let less of the carbon get away, you can select the bacteria and change the conditions under which they're working to emphasize hydrogen production. Or you can go one better. You can make all of the bacterial activity under more closely controlled conditions and just separate the enzyme, the essential enzyme, hydrogenase, or another enzyme that is similarly able to break hydrogen off of hydrocarbons, and use just the enzyme in a high surface to volume ratio preparation of your wastes, slurry, and stir them up and keep the enzymes working. Or you can park the enzymes on substrates that do this job even better. Or you can graft them to polymers, such as polymer beads, and circulate them and get a lot of exposure in a rapid production of hydrogen. So yes, the answer is there are great investigations going on. Some of them are extremely practical on the basis of methane generation from sewage. And the road is open for your activity in improving on what's been done. But mostly I would encourage you to look into the practical measure of using solar energy to provide the optimum temperature and using common chemistry to provide the optimum pH and chemical conditions for increasing hydrogen production from sewage and garbage. And I would emphasize, most of all, to do so in a way that keeps the carbon from going into the atmosphere. Use the carbon as a building block.
What is the current, what's the best amount of methane, what's the best conversion of methane now, other than just straight methane that's reduced so you can convert it to hydrogen?
Well, this is a most interesting question. The implication of the question is, do you have to go through methane? And the answer is no. In fact, when you really do the analysis on how methane is formed, you find that hydrogen is produced and then added to precursors to make the methane. So if you change the conditions of operation, you can release the hydrogen before the methane is made.
Because methane is one of our biggest concerns. Right?
Methane is one of the biggest greenhouse gas offensive constituents. I would also say in that regard that it's well worthwhile to consider letting the methane come to you and then dissociating the methane. And you might look to Pyle as a person that would give you some information on how to dissociate methane, just as he's been dissociating water vapor by direct heat from the sun, concentrated heat from the sun. There was another question over here, please.
I was just going to say that in Michigan, in Ovid, Michigan, we have 1,000 head dairy herd farm there, that they're processing the methane from 2 large tanks with kind of a rubber bag over the top of it. So they're not using the solar, they heat these tanks to optimum around 90 degrees. They're running 3 6-cylinder gas engines that are turbocharged, running a 100 kilowatt generator each. So that's 3 100 kilowatt generators running 24 hours a day from 1,000 cow herd. And so it just kind of gives you a feel for what you can do with, and this is really basic with standard microzones. There's no specialization here, so it gives you a starting point, a feel for what can be done.
Now, I would mention that in this example, you have the production of electricity, the methane is removed from the wastes, and carbon dioxide then is produced as a result of burning the methane.
Yeah, so you still have it.
So you still have the carbon dioxide. You have about 12 pounds of carbon going through the engine for every 16 pounds of methane to form carbon dioxide. And so as a net, you get rid of one of the more active greenhouse gases for a less active greenhouse gas, but you have still the carbon going into the
That's
atmosphere.
only a 25% improvement actually in releasing it.
That's about right.
But that's all carbon that had been removed from the atmosphere in the first place.
That's true. The observation here is that these are organic materials that are being used. It is a very good process that's involved by making some electricity while it goes into the atmosphere. It's better than just letting it rot away and go into the atmosphere without some good being produced.
Yes.
And so in that regard, it's very favorable to run biomass for steam generation and making electricity, or biomass for making fuels, as in an IC engine, and making electricity. It's also important to note in that regard, and I think that it's well worthwhile to mention at this time, that the way that you could be converting that methane is in a fuel cell for a much higher efficiency and making even more electricity. And high temperature fuel cells have arrived. It's possible now to put natural gas or biomass methane or hydrogen into high temperature fuel cells, and if your purpose is simply making electricity, that's a very good way to improve on heat engine efficiency. Another topic, if we're done with that one, another topic that I would like to move to is making electricity for purposes of electrolysis or for other applications of electricity from solar energy through a concentrator and a heat engine. The technology is solar dish Stirling technology. And I brought a working example with me to show you the simplicity of this technology. It consists of a parabolic reflector that concentrates solar energy to this area. And at this area you heat a working fluid such as air or hydrogen and use it to expand on a piston engine. And the piston engine then is the rest of the apparatus. And you can then wind a portion of this engine for purposes of producing electricity. So you have a engine generator, just as you mentioned with respect to the engine generator that used the dairy methane as a fuel. Instead, this uses solar energy as the input energy, and you get out electricity, with which you can use the electrolysis technique, or you can improve on low temperature electrolysis by using some of the waste heat to elevate the temperature, and in any event, you make hydrogen. The process efficiency in this regard is rather remarkably high, surprisingly high. The portion of solar energy that falls on this disk and is converted into shaft power ranges up to about 30%. It's abnormally high compared to other selections, other choices that we have. And as the rest of the story goes, you would follow the same picture that Peter Lehman showed. You'd have about a 60 or 70% efficiency.
If the Stirling engine is actually only 1 or 2%, you came up with this much higher figure. Is that because you don't count the energy from the sun, or how is that?
No, well, let me just say the efficiency of Stirling engines is well known to be, with regeneration, in the 40% range. Now, demonstrators like this, I think that this may be what you're referring to, demonstrators like this have the problem of being too efficient. If they're too efficient and not loaded, they melt. If you're not taking the energy out that you're collecting, you melt this thing. And so devices like this are a balance between making something work for demonstration and getting rid of the rest of the heat so you don't run the device. If you build one of these from scratch, you run into this problem. You learn all about engines, you make it efficient, you put it together, you crank it up, and it melts.
I tried to put a load on this. I have this at home too, and it just has practically no energy.
Let me tell you how to improve.
It goes it runs at 400 RPM, but there's practically no energy.
Well,
Roy, let me make a comment.
Sure.
That's true. This is pretty much a toy engine. If you use a really well-developed, well-engineered Stirling engine, you get much higher efficiency.
There were actually Stirling engines which were used here between Willits and Eureka along the Southern Pacific Railroad.
Right.
They were heated with wood to pump water into the tanks for the steam engines which used to operate here from 1920 to about 50.
Well, those are more efficient.
But I thought the efficiency of those was also estimated to be only 2 to 3%. So maybe I'm wrong.
That could be, but they're much better now, actually.
It does have 70%.
But I think the ones which are much higher efficiency, they are much more complex to be built. They use all kinds of gadgets that have to work in a vacuum and things like this.
Well, I'll tell you what, just to help you with your engine, let's look at what you can do to this one to make it more efficient.
Yeah, all right. Good.
All right, let's look at this very one to see what you might do with your engine to make its efficiency higher. Number one, you need to reduce the way it loses energy. This one's looking at you, the way it loses energy. All of this area is losing energy. it's receiving energy from the focus on this cylindrical portion, but this disk is radiating energy into the sky just as a radiative loss without check. So the first thing you might do is just to put an insulator on this area right here. That would help it a lot. The second thing you might do is to improve the absorptivity to emissivity ratio of this area. You can do that with coatings. But I caution you, if you start that, it'll probably melt right off unless you do something on the other end to take the power out that you're gaining. The other thing that you might do is to house the system within a hermetic seal, so you could change working fluids from air to something that carries a lot more energy away, and that would be helium or hydrogen. Pick a much higher specific heat material, and you can carry much more energy to the working piston and make the efficiency much higher. But those two things are easily done. You can do them yourself, and if you do, be sure and add one more thing. Add a way to take the energy away, or you'll surely melt down. Students that I've helped in improving the efficiency have been very, very interested in the very topic that you brought up until they melted the system or oxidized the target. So you have to take care of this further question of getting the energy out and delivered to something if you're going to make these efficiency improvements. Another, please.
Is all that heat necessary? For instance, you're using a parabolic shape, so you're getting a focal point. Perhaps if you use some flat surfaces to create a focal length, you could use lower heat. You could get lower operating temperatures.
The idea in that regard is to reduce the load on the materials, or reduce the oxidation characteristics, and make it last longer by reducing the temperature. And yes, you can definitely do that. You can fuzz up the focal system and make the system, so far as receiving energy, more rugged or less damaged, I would say, over the course of activity.
The question I'm asking is are you
why do it?
Are you losing the whole ballgame by taking that focal point out of the length, thereby lowering the operating temperatures, or therefore losing what you started with?
Yeah, I'd much rather improve the taking away of energy, because that's what you're looking for, is useful energy, than to fuzz up the focus. Be a much more successful thing for making hydrogen out of the same shadow or the same amount of solar energy that you have available. Please. There was another question right here. Did you have one on turn? Right here, please.
What's the specular efficiency of that particular parabolic mirror?
Well, it once was about 80%. It's gone much lower as it's been hauled around and made dirty and got scratched up.
What's made of?
Well, stainless steel.
Just a polished stainless steel?
It's just polished stainless steel. But I might say in that regard that if you wanted to improve your efficiency, that would be a good thing to look at. You can preserve these by keeping people off of them and keeping your hands off of them and not scratching them and what have you, and they do much better. It's also true that you can improve upon that by putting coatings over the stainless steel that will keep it from being oxidized or scratched and make it much more cleanable. And in a practical world, and I think that this is what this audience is looking for, that would be a very good step, because the bother that you incur by keeping this working involves how you keep it clean. And so making a glass surface or a polymer surface that's easily cleaned is well worthwhile. It facilitates making this system last for you and making it work more efficiently. Another topic that I'd like to move to besides this mechanical system for producing electricity still involves the dish. And it is to look into the use of the dish with biomass or waste materials as a means of decomposing the hydrocarbon into just carbon or carbon-rich substances and hydrogen. This is a more direct route, and it really looks more like the route that Pyle was telling you about than the bacterial approach where you use enzymes to break the hydrogen off of the hydrocarbon. In this instance, you do just what the toaster does to bread. You take enough high temperature energy on the hydrocarbon to break it. And the toaster is an illustration of a sufficient temperature to do this. The incandescent temperature of the filaments in a toaster drive off the hydrogen. The dehydrogenated white flour becomes brown, and you call it toast. If you run the toaster in a vacuum chamber, you can produce hydrogen. You can collect it. So can you do it here. You can use solar energy in a much higher quality form to dehydrogenate anything that ever grew and collect the hydrogen and operate without enzymes and save the carbon that's left over, and it'll be much the same form of the carbon that's being passed around. Where is that carbon now? That carbon right there. In process chemistry, this is a very good thing to do if you have solar energy and want to avoid the smell of the operation that's usually attended the bacterial approach. This becomes a way that you can add other chemicals that are getter chemicals for what you don't want, such as the sulfur or the halogens. And so you get them as precipitates, or you collect them at least, instead of having them in the hydrogen train. And so you can clean up the operation using thermal energy or solar energy as the driving force for the reactions. Please.
I've got some interest in organic gardening and stuff and making compost, basically. In that process, if you do it right, it doesn't smell bad. And I'm wondering, does it preserve the hydrogen in that case? Do you know?
Oh, this is the most interesting question. Did everybody hear the question? Where does the smell come from in the processing of organic materials?
Anaerobic bacteria.
Like bacteria.
It really does. And so if you want to denature using solar energy at a sufficiently high temperature, you can get around the smell right away.
Aerobic bacteria oxidate the waste.
Even higher, yeah. But you can, incidentally, the second question is how about then going back to, after you've denatured and killed everything that was there, how about peeling it off and adding a process?
Aerobic bacteria and oxidate.
There you are. And get rid of whatever else was there. Well, I'd rather, if you want to keep the atmosphere from having a carbon load, I'd rather not do that. I'd rather just get the hydrogen off, then go to carbon chemistry. And make things like this next sample that I'll pass out, which is a form of carbon that is the next step, next higher value step from the granules that went around before. These are fibers. These fibers of carbon are stronger than steel, and they don't corrode, they don't rust. You can make your fenders or your rooftops or whatever you'd like out of these materials, and they can be extremely strong and weather resistant, UV resistant. And this is a much better thing to do with your carbon than having it go into the atmosphere as a greenhouse gas.
Is that right now a fairly complicated process to make carbon fiber?
Well, there are many routes to making these. Some of them are amazingly simple, and some of them are largely by aid of little guys, by microorganisms or macroorganisms. You can think of things that make silkworms. That's exactly right. You can think of things that make filament and employ them in this process. Most of the filaments that spiders and silkworms and whatever you make can be dehydrogenated into this material. So you go out and employ a lot of silkworms, run the silk through the focal point of a point focus system, and this is what you get. Please.
I just had to finish the one thought I had on that composting. Does that put carbon into the atmosphere?
Yes, it does. The ultimate of composting is to have water vapor and carbon dioxide go away, so you reduce the quantity of material, and so every year you don't grow a bigger heap of compost.
That's carbon that's leaving there.
And what's leaving is carbon. And by and large, what we get rid of when we say we're disposing is carbon dioxide and water vapor. The largest quantity besides the deaeration or the dewatering material it leaves is carbon. It's carbon something. It's carbon dioxide, or it's methane. But it's carbon that we're getting rid of.
Do you feel guilty of composting stuff?
Yeah, my role today is to make you feel guilty for putting carbon in the atmosphere. If you feel bad about putting carbon in the atmosphere, then I will have succeeded, because that gives rise to doing something with carbon that's better than wasting it, and it also gives rise to doing something with the hydrogen. What you'd like to do with the hydrogen is drive your car and feel really good, because you can run a minus emissions car. The more you drive, the more air you clean. Please.
What happens to the carbon fiber when you're done using it? I mean, like when it's becomes trash.
You recycle it. It's really recyclable. If you want to look at the energy of recycling, here's your star. If you want to look at the energy involved in getting this back into a useful form, this is just about the best thing you can do. It doesn't rust and fall on the road when you're going someplace. And when you get there, you have a much lower curb weight than with steel. And so you'll have used much less hydrogen, and you'll have used much less of the Earth's stuff to make the hydrogen if you go to this transportation system. And then after you're done, it's very low in energy content to recycle it, to reconstitute it. Please.
Can you go through a simple process of using a high temperature to make garbage? Carbon pellets in your hydrogen?
Right. So what you do on this end of the machine is make a hopper. And you put in your orange peels and paper and anything else that no one wants.
How about plastic?
Plastic.
Really?
Yep.
What about sewage?
Yep. Do I? Oh, let's keep those. Well, you can. If you know that they're coming, we'll handle them. But you wish for all the world that you didn't get a lot of materials that can be made into gaseous organics. You know, it can be the metals, heavy metals, like the metal organics that will go away in incineration and what have you. But if you know they're coming, we'll accept them too, because we're going to win them back. We'll separate them by extraction processes if they're there. But by and large, you just make the hopper, and you auger from that hopper into this focal plane. And you dwell long enough for these reactions to occur. And by and large, these are dehydrogenation reactions. They're the same as the toaster. You put them there, you shine lots of photons on them, they get hot. They rattle off the hydrogen, you collect the hydrogen, and what's left is mostly carbon. Now, if the carbon has a lot of heavy metals and what have you in it, then you take it to a further process and separate, either by leaching or by bubbling something through with a surface active agent to collect these materials, a froth. You doctor that off and process that to refined metals if you want to get them out of the system, and that's a very good thing to do. You take the very same route that produced them originally from the ores. And now you have a clean atmosphere absent the carbon dioxide production. You have the hydrogen as a currency that you can use in chemistry or in transportation and in countless other ways. And you do this at the expense of solar energy that was going to waste anyway. So you've taken waste, 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 and added them up to goods, goods, goods. Good thing to do.
What do you have to
Please.
What would you do with all the carbon you would accumulate?
Oh.
You know, say you got a whole vat full of garbage, and you run it through your machine of that sort, and then you get all the hydrogen, now you got this carbon.
Good.
You have more than carbon.
Well, wait a minute. Let's start with the carbon. Let's stay with the carbon. On the carbon, here's what you can do. You can make activated carbon. In fact, that's the first form that you get is very activated carbon. And you can use it to filter the air or to filter water. Or you can use it in industry for all of the ways that carbon is now going in as a precursor to some chemical or some other good. You can make carbon fiber to reinforce materials that would be the new materials that are much more successful in withstanding the rigors of the environment and providing low curb weight because they're stronger than steel. And you can make diamond plating. One of the most exciting things to do with carbon is to plate materials that you don't want to lose. You can plate Caterpillar components and they'll wear much longer. You can plate things that are chemically susceptible to corrosion. These are corrosion-proof platings. And they can be very, very thin and transparent. And they can also give you remarkably pleasing new optical qualities, properties that have to do with controlling the reflection and have to do with controlling the refraction. These diamond platings are just remarkable in the jobs they're able to do and the improvements that they're able to make. And you can also use the carbon as a more gross building block, and a very valuable building block, I might add. Carbon blocks are very inert and can very successfully contain other materials as melted materials, as in metallurgy and in casting of other metals. So they're a very good application for carbon. We're short of carbon, and if you want to produce a lot of carbon, this is a valuable economic good and a job development opportunity. So we're not going to make too much carbon, and it's much, much better to have these products, these valuable products, than to have the carbon go to waste as a greenhouse gas constituent.
But as a consumer, or as a person who manufactures carbon, yourself or me, how could you or we make this useful?
Knits and socks. Carbon socks last a long time.
Can you modify the aerobic bacteria to produce hydrogen rather than methane?
Yep.
And then you could get your process going right in the beginning, you know, by just low heat to let the aerobic bacteria do their work.
Here's an invention.
Wait a minute,
we've got an invention.
Fertilize
Okay.
it, grow mulberry leaves, and then you've got your carbon fibers right
I don't
there.
know if you're noticing the process that's happening, but we've got an inventor right here, right now. He's making a combined cycle system. He's going to use solar energy to do some high temperature stuff. He's going to use solar energy to increase the microbes. And he's going to come up with a system that doesn't stink, because he's going to take out the things that can stink, the sulfur and what have you. The thiol compounds aren't going to be produced in his system. He's going to eliminate them as he goes, so that the subsequent processes are much more pleasing to anybody that has to be around them. I don't know if you noticed that chemistry or not, but right there is an invention. Give that guy a star. Okay, well, if that winds it up on these solar thermal processes, let me go to another one, please.
Well, if they're so basic and simple, why doesn't the state of New York just ease up?
Well, I don't know. I think that they're getting close. I think that we're finding a much greater receptivity, because there isn't any place to put the garbage and sewage anymore.
Yeah, I mean, if you can burn stuff, everything that goes into the dump sites, I mean, it's a valuable fuel, so it wouldn't be wasted anymore.
It's absolutely true. Anything that could have been dried out and burned can be made into much more valuable things by dehydrogenation and carbon chemistry. And you know, by the way, you can do that in sequences to make it much more pleasing to yourself and everybody else that has to be around. Please.
Roy, before you get off the subject of heat engines, this is, I think most of us here are interested in generating electricity from the sun. A lot of us here are anyway. And you've been a little bit reticent to talk about what's commercially available. You can't generate electricity much from this thing that we can use, but there are some things around that you can. You want to talk about them, or?
Yeah, I really would.
In fact, I would pose a question to the audience, maybe. If there were a technology available that were cheaper than photovoltaics by 50% or 2/3, and twice as efficient, would you be interested in buying some of it?
No. You know why? Because it's mechanical and you have to work on it.
It'd be mechanical, yeah.
And you have to work on it. The thing that photovoltaics has got for it right now is you can install it and you can hand it down to your grandkids, and you may only have to check the water and the batteries once a year. So the initial cost is not always the problem. The long term, long range, we're looking longer range these days, I hope. So
I think that's a good exchange, and I
Yes.
think that that's a good market survey on what we're looking for. We're looking for things that are convenient And we're looking for things that last a long time finally.
That are maintenance free.
And we're looking for jobs to do maintenance so that other people can think that they're maintenance free.
They don't stink. They don't stink.
And we're looking for things that don't stink.
Long-lasting socks.
Yeah, that's right. Anyway, you know, it's well worthwhile to take these lists of, this wish list right into account. There is a dish that lasts 40 years. It's a glass and steel dish. And it is able to drive these processes, these thermochemical processes, or drive a Stirling engine for low-cost, renewable electricity production. You can use the electricity as you will. You can run a lighting system. You can run a very efficient lighting system. You can run the engines or the motors of industry, and you can make the industrial revolution run without burning 180 million barrels equivalent of fossil fuels a day. It can be done with dishes that run engines that produce electricity, engine generator sets that produce electricity. And by the way, we can do this out of resources that we have from the Industrial Revolution. The resources are the trained people, the pipelines of materials that now flow into commerce, and we can do it at a lower use of materials that the earth has to give up than other systems that are in competition with it or that are being considered with it. In other words, if you take the all-in cost of what the earth has to give up, this is a system that comes out very low. Not quite as low as the bacteria processing the garbage and the sewage, but there isn't enough of that material to support the present population. We don't have enough biomass material to support the present population if we turn to biomass for our fuel and did it in the most efficient way. We just don't have that much. We've made the population and the expectations of the population so large as we've depended upon fossil fuel to make it that way that we couldn't go to biomass to substitute and come out in the same way that we are right now. And we couldn't even begin to extend to the larger populations of the world that haven't tasted yet, but have watched and become more jealous by the day of the American and European standards of living. If we're going to extend those standards to the third world, we have to do so with a much more efficient regime of materials and applications such as this than we've been doing with the fossil system. Please.
I would just like to say, if it wouldn't have been for some of us with vision, we would have a big biomass plant right here, about half a mile behind this building. But we decided our forests are already too far depleted, and said we can't even use these last remnants of it to be made into energy. And that was a big fight in this community about 2 years ago. And fortunately, the plant has not been built, but it was hinging on one road.
Please.
I want to talk about sponge iron as a source of hydrogen.
Yeah, I would like to talk about sponge iron as a source of hydrogen. One of the ways, and this will get us away from this topic for a moment, and if anyone wants to really know more about dishes, why that's a topic that is dear to my heart, and I'll talk about that in more detail later. But let me try to cover the board as promised, and sponge iron is one of them. First, you make iron. You make iron by any of a lot of different techniques. You can take iron ore, and or you can take wrecked automobiles or tin cans and what have you, and make iron. And then you can react the iron with water and make hydrogen. The reaction is Fe, or iron, plus water, H2O, gives some oxide of iron, FeO, Fe2O3, or Fe3O4, and hydrogen. And this has been used extensively to produce hydrogen in the past. In fact, many of the ways that dirigibles were fueled, or not fueled, that were filled with hydrogen was by the reaction of steam and iron wool, or sponge iron. And that simple reaction is a good reaction, is an expedient reaction to produce relatively pure hydrogen. And so you can think of this as a combined cycle where you operate the iron purification chemistry, hopefully with solar energy as your heat source and some reducing material. And the reducing material can be hydrogen. It could be hydrogen from biomass. You produce the iron, then you react the iron with water and produce more hydrogen. And it's a very good way to produce quantities of hydrogen rapidly. If you run the temperature at a high temperature, the kinetics are very high, and you get relatively pure hydrogen production without the need for further train devices to qualify the hydrogen.
What now do you do with all the oxides and the rust?
Well, you put it in pills and send it out for making you feel better. Or there's a lot of applications. Or you can recycle it to places that are solar rich. And they
recycle it, you've got to get involved with carbon once again. Now you're going to produce carbon dioxide. That's what you don't want to produce.
But you don't. You can run all of the iron chemistry on hydrogen. Right up to the point where you have to add some carbon to get the qualities that you're looking for in steel. You can do it all with hydrogen as a reducing agent. You can go backwards in that reaction using heat, and it can be solar energy as the heat.
But you can't use hydrogen as a reducing agent if you got into this pickle in the first place by using it to produce hydrogen.
Oh, yes, you can.
We're not involved with perpetual motion.
Oh, yes, it is. This turns out to be perpetual motion in chemistry. All you do is change the conditions of state, and you can run this as a cycle. One day you run the cycle of reducing the iron oxide to iron with hydrogen. The next day you run the cycle of producing hydrogen from iron and water. It's an interesting
fact to have.
Is there a gain?
Well, no, there's a loss. You have to put energy in together. It is not perpetual motion, but it's using the same chemicals over and over again. So you think of the chemicals as a belt, and you run this belt with some energy input. And the energy input can be solar energy. But it is most curious that you brought up this question, is that perpetual motion? Well, you always have to ask that, because oftentimes, and we run a laboratory at the American Hydrogen Association to pick and choose among those that are perpetual motion and those that have a chance. And we get a lot of perpetual motion applications. The telephone rings often, and the idea is this. Don't tell anyone, but we're going to run our car on hydrogen. And we're going to produce it from the alternator. We're going to run the car on hydrogen, we're going to produce it from the alternator. And so you listen and you hear this again and again. So by now, here's what we say. There's an easier way. Just put small tires, small wheels on the front of the car, put big ones on the back, and go downhill all the time.
Going a little more into the details, turning the iron into hydrogen, you just don't dump the water on. Something else is going to happen. Now let's hear some more about this.
All right. Well, it is a little more involved.
Explain that it's being considered as a storage medium.
It's true. The way that this was done in history is the way that the Germans did it very well. What they realized was that they had a higher efficiency in the production of iron than they had in their electrical plants. They ran, if you think of the steel produced or the iron produced as a fuel, they ran efficiencies that were over 50% in the production of the fuel. The way they did it was by doing a lot of recuperation and regeneration. And they perfected that to the point that the value in the form of energy in the steel produced was about 60% of the amount of energy that went into the process. So they said, that's pretty good. That's better than running the power plant on a Rankine cycle and getting a 30 or 40% efficiency. And they were right. That's what drove them to think of this as a way to use iron as a fuel. And it's the way we should think of it again. So what you do then is this. You make the steel by reducing the ore. Then you use the steel to react with water to produce the hydrogen. And in that sense, you simply make a very high surface to volume ratio. You make the steel very available. You make it accessible to the water molecules. And if the accessibility is high, and you can find this on lots of surfaces that you're familiar with, some of which are very dear, you take a good saw that's been carefully sharpened and what have you. And you'll find that the place where the water attacks it and rusts it is where it's been most activated. You clean it all up, it looks bright and shiny, you sharpen it, you have a lot of edges, and that's where it's attacked by the water. And you can produce hydrogen. You can find the hydrogen even at low temperatures. If you want to accelerate that, you make it into steel wool.
That ain't the way they used to do it for my stove at home, though. They had a hot plate with a cold fire, and they dumped water on it. That made hydrogen. I don't know how good. I think it was a low grade.
Here's
That
another.
heated the whole town.
Here's another process. This isn't from steel, but this uses a steel container. This is the water-gas reaction. This is a process that, once operated for the purpose of having some 400 cities use hydrogen, albeit dirty hydrogen, as a preference to coal or wood, so that you could have clean lungs and hydrogen lights or hydrogen cooking or hydrogen heating. The name of the process was town gas production, or city gas, or carbureted gas, or blue gas. It had a lot of names. But it wasn't the iron process. This instead was the process of reacting carbon with steam to produce carbon monoxide or carbon dioxide and hydrogen. Usually they left it at just carbon monoxide and hydrogen. What you received at the other end was a dirty form of hydrogen that could kill you. The carbon monoxide could poison you. And when the comic strip ran this depiction of somebody committing suicide by putting their head in the oven, it wasn't the hydrogen that was bothering them. It was the carbon monoxide. And it came as part and parcel of the process called the water-gas reaction. It was improved upon, and the carbon monoxide was then used, often with catalysts, the aid of catalysts, to produce more hydrogen. So you got carbon dioxide, which could be separated, could be condensed and made into carbon dioxide products.
How did they separate it in the old days?
By cooling it. By
heating it,
Yeah, well, they separated it by cooling until the carbon dioxide came out.
They closed that plant down before I was old enough to understand what was going on. But it was right behind where I later owned some property, and it was all contaminated the other day. They had a big job cleaning it.
Well, I don't doubt that, because the coal that came through carried a lot of ash. And the ash that was left over was contaminant to the area.
The city owned the property, so it cleaned a lot faster than if UI owned it,
But that process served a very large population very successfully until natural gas came in. And it, by the way, was a process that was subsidized by the federal government, at least in this continent, and made it happen very rapidly. When FDR heard that there were a number of robber barons that were controlling this city gas production, he moved against them and said, look, if you've got natural gas in Texas, we're going to make it easy for you to get it to New Jersey and to New England. And so he made a federal program that nationalized finance or banking, agriculture, and energy. So the three things that he nationalized on taking charge of the country that needed some guidance were these issues.
So that's why we have nuclear power and coal power in Louisiana now. And it's cheaper to get natural gas in Boston than Louisiana.
Eventually.
Okay, I was wondering.
Yeah,
eventually. Did that for us.
but that's the routine. That is the way it happened. I'm running out of time, so I'm going to pick up some other subjects, but I'll take a question, please.
Would you comment then on the political dimension of this whole transition?
Let's 30 seconds.
Well, let me just say I can't, because the American Hydrogen Association is a non-political organization. We don't know about politics. But I would say personally this. The time is right for a leader, whether it's a political leader or otherwise, to say, look, we have depleted natural gas fields that we can store hydrogen in. We can put the hydrogen there. We can take it to market from those depleted fields. We have lots of things going to waste that can be turned into hydrogen, this hydrogen currency, or electricity, renewable electricity. And we can use them to have prosperity without pollution. Those are simple things that a leader could be doing right now. They mean jobs. They truly mean a better environment. They mean taking advantage of things that we have, such as depleted gas fields that have been for some 500 million years very good seals for holding natural gas. They'll hold hydrogen. And we can take our engines of progress, our jet engines, our car engines, our industrial engines, to the very same tasks and do the same work with hydrogen as they've been doing on diesel fuel or gasoline. And we can have, and I say it again with real intent to have it in our lifetimes, prosperity without pollution by this adaptation. That's a non-political statement.
Why
Those
don't
are
we
just
have it now, though? Why not? If it makes
No
sense.
leadership.
Yeah.
There's
Too much private interest.
Well, the reason that we don't have it right now, and this is my opinion, is because we don't have sufficient education, awareness of these opportunities. If we had a more pervasive educational system on these topics of alternatives, we'd pick good alternatives. As consumers, we'd be asking for better alternatives. As manufacturers, we'd be sending them. We're just not sufficiently educated to make the right decisions. And to demand then, by our consumer habits, by what we buy, by our orders, the right thing.
Aren't the Japanese developing this to a greater degree than we are?
The need to respond to international competition has been brought up, and it's here. The people that are much ahead of us are the Germans, the Japanese. Saudi Arabia has announced that they're going to supply 25% of the world's energy in the form of solar hydrogen. So so they have realized that someday it's going to be important to the consumers to not stink up the planet by burning something that's made out of carbon and something. So they're going to supply something that's better. It's clean hydrogen. They're going to run out of fuel too. Please. A book that lays this out is the Phoenix Project that is shown here. It's a book by Harry Braun. There are other good books that are also on the same topic. One's by Joan Ogden. We offer it. And we have another book, Fuel from Water, that is a very good reference to the topic. Here's a book by Roger Billings on the very same topic of how to make and use hydrogen safely. Fuel from Water by Peavy is very good reading on the topic. But these are the sort of educational aids that should be commonplace in everyone's home. It should be something that you could hand out to the neighbor and say, look, here's a better way to run the Industrial Revolution.
Why don't you send a set to the White House?
We're a non-political organization, but we have an educational extension of our activities sent to the White House. Please.
As an economist, there's an input-output model that explains the politics. The input was cash contributions from the oil industry into the campaign to re-elect President Reagan and Bush, and the output was killing the solar subsidies and all sorts of solar energy programs. I don't know whether you want to attribute a direct connection. I would.
Well, we've talked before about private sources of funding for large-scale solar hydrogen projects. On a world scale, give people an opportunity to invest their money into clean air bonds. Can you speak about that a little bit, and also about a specific project, perhaps, that those types of bonds could go toward creating an actual electric utility based on solar hydrogen?
Now, there is good government leadership at work right now in America, and it has resulted in an offering that's been made through the Department of Energy. And the offering says that we will match however much private industry can put together to build solar Stirling dish generator systems, solar thermal systems. In other words, if you can come up with $100 million, the Department of Energy will match it for the purpose of making a system that the utilities can use to make renewable electricity. It's an extremely good offer. One way to bring up the matching fund portion from the private sector is through bonds, or stop or other ways that investment can be made. And I think that this really comes to the heart of whether or not we really wish a better world or not. If we wish a better world, we need to invest in long-term projects that will do it. The offering by the Department of Energy makes it so that they don't have to be such long-term projects as they would be without the fund matching extent that they've brought into light. This is an extremely good offer that needs to be looked into by investors, needs to be pursued if you want to make a better world and make a good return on your investment at the same time. The idea in that regard, and I'll just explore it further on a world basis, is very worthwhile too. On a worldwide basis, and we're all members of a world community, we really need to look to the populations of the world that need a better standard of living, that have looked at our standard of living with envy. They've said, why can't we have our resources go into what you've been doing? And our answer to them is, well, there isn't enough for us to keep doing what we're doing and have you do it too. It's a very bad answer.
I think the other point is they don't have an infrastructure based on oil, and just starting out with this clean slate, it makes logical sense to analyze everything available and pick the most appropriate one.
I think this is a very good point. We need to help in an educational way those emerging countries avoid the inefficiencies that we have adopted.
Precisely.
We should help them avoid the inefficiencies that we've gone through. And we should say to them, we're ready to export the technology. You select from everything we have and anybody else has. Pick the best one. If it's ours, we'll bring it to you. And we're glad to do that because we want a better environment as a result. Those are the trade-offs. That's the commerce that can develop, and we should be out getting it. This runs me over the time that's available. I don't know if you want to pursue
The next session doesn't start till 2 o'clock. If nobody cares,
All right.
you can
I'd like to touch on some other topics, please.
We've got a very efficient heat engine going on in this building right now. I wonder if we could expel some of the excess.
We can try. I know I'm going over time, so feel free to go about your business if you have someplace else to be. Please.
Could you briefly describe how the Stirling engine works? I've heard of it, I've read a little bit about it, but I forget exactly how it works.
Well,
and I might have missed some previous thing where we talked about it.
Yeah. Well,
same here.
Yeah, okay. The question is, how does the Stirling engine operate?
Can I just ask one question while you were still on the topic of politics before you totally switched?
We're not talking about politics.
Well, I'm sorry. I wasn't really into politics so much as the transition.
Yeah, okay. We're talking about, that's right, we're talking about the transition.
Yeah, and why industry isn't playing a role. I think the biggest problem has been lack of market, perception. Is there being a market? I'm not going to invest money if there's no market. What is the catalyst to bring industry into an position of acting towards that end? And as we know, it's been a problem in transportation fuels and other areas. What is your comment on getting industry to commit itself to that money with or without the government plug of money to make the transition in reality?
Let's look at two cases. I don't know if everyone heard the question or not, and I'll pick up the other question in a moment. But the question was market development for clean energy, if I might just say it in that way.
Sure.
The question is, how do you develop a market for clean electricity? How do you develop a market for clean hydrogen to replace hydrocarbons? I think that the answer is twofold, as the question went on to suggest. It's one with government assistance or government subsidies, or with government whips in the form of laws that say you cannot pollute, or we're going to make a carbon tax. Those are the government side of the picture. But there's another one. The other one, I believe, is through education, and it's through business managers picking a course for the future that is more prosperous, that makes more profit, that makes better working conditions, that they will identify with and use in their advertising for more goodwill. I believe those are the ultimate ways that you succeed beyond government assistance or intervention. Now, it may take some carbon tax, it may take some other spurs to start this, but once you have started it, the spurs aren't enough to make the horse do it. The horse has to have the energy within to carry the load. And I'm talking about the horse being the economy.
Wouldn't you have to kill the subsidies on the oil and nuclear to make that happen though?
Well, let's look at what they are. The subsidies that we presently have are said to be more than $60 billion per year for the status quo nuclear and the status quo petroleum system, the fossil fuel-based economy. I know they're much larger than that when you take into account the cost of maintaining a fleet to ensure our oil supply lines. I know that they're much larger than that when you take into account the cost of dealing with poor health that starts by the age of 12 and having 15% or more lung dysfunction. I know that those costs are greater than $60 billion per year. But even at the point of $60 billion a year, compare that with the present subsidy for renewables, or the present subsidy for solar. They're minuscule. We're talking about $3 million a year in the U.S. It's minuscule. It's almost humorous to compare the two. They don't even compare. There's not a scale factor that you can apply that makes them right. They're not right. But I would say this, and I think that this is the important thing. There's something much more valuable, there's something much more successful than going to some governmental agency, state or federal, and saying we're not getting our fair share. It's much more effective to say instead, we know what we're going to buy, we know what we want, and you can write to the guys that are making cars or stoves or air conditioners and say, we're a market for a better product. And that's a much more direct statement than to have the government tell them later on. You can tell them tomorrow the postage is 2 bits, and you can get an effect out of this. And I think that ultimately that is the way you activate the horse. You can have some spurs if you will, but it's much better to feed the horse, make it strong, and win with it. So it's a win-win situation.
What's your political voice? Question.
I've got to believe that the way that you express your buying habit is going to have a much quicker and much more sustainable influence for your good than to spend your time talking to a politician. I believe that. I think that you're able to have a bigger influence quicker by saying, I want to buy a stove that burns hydrogen, or I want to buy a stove with a coefficient of performance of 3. So however much hydrogen I use in it, I get 3 times the heating effect by a fuel cell driving a heat pump.
Buy American.
Buy American. Whatever you choose to say, I think that if you say that to a manufacturer that can serve your purposes, you'll get a quicker and more lasting result.
You know, I heard today that the energy bill, though, says it supports all forms of alternative energy except for hydrogen. So, I mean, that's a major block right there, and, you know, where the...
I cannot say that I'm happy with it. I'm just saying that in spite of that, you can have an effect, an immediate effect. I'm not happy with it. I think it's a bad deal.
Totally.
If you really want to know what I think about it, it's terrible. But then am I going to waste any more air about that? Not at all. I'm going to make a car that runs on hydrogen and cleans the air. I'm going to give a power plant choice. So your next power plant is going to be a renewable electricity power plant from solar energy.
Will you do your hydrogen car through internal combustion?
Yeah, well, the question is, how would you run your hydrogen car? The answer is, we have 400 million cars out there right now that are an opportunity to do something positive. And the most positive thing that you might choose to do at the moment is to burn hydrogen in them. And if you do, you can clean the air. So they can become minus emissions cars. They're better than zero emissions. They're minus emissions cars. You can drive and clean as you go. It's a much better deal than just waiting for the next decade or so for the electrics to come in, or for the fuel cell electrics to come in. You can run internal combustion engines now with hydrogen and have the result of transportation from your existing car and provide the service of cleaning the atmosphere as you go.
You ever heard of an internal combustion pump?
I guess not. Is it an internal combustion engine driving a pump?
No, it's basically gas expanding, pushing a piston which pumps.
Well, I have heard of such a device.
I never have it, I would love to.
There are devices such as that that will provide air conditioning directly from an internal combustion engine process or from an external combustion process.
And this is like for a hydraulically driven car.
Well, another invention. Roy? The second star.
To answer that question on the Stirling engine, the backside is blackboard clear if you'd like to use it.
All right.
Make it flip over.
Okay, good.
There's some shock there.
Good, good. That would be very helpful. Oh, it's going to be tough.
Well, let's turn it down. I'd just like to say, while there's a pause here, that these books that we held up are all available here at the fair. The American Hydrogen Association has the Phoenix Project and Tool from Water. If they run out of copies, you can order them through the Alternative Energy Engineering catalog, or Real Goods, I believe, has some of them. And Roger Billings' booth has these available.
This device, if you look with X-ray vision on the inside, would have these components. Inside would be a piston which is loosely fitted. And I marked it D because it's nothing more than a displacement device. What you use it to do is to occupy a volume. And when it occupies that volume, it displaces the fluid that's there to another place. In this instance, it displaces the fluid that's there to this space. Another piston that you'd see if you had X-ray vision is a power piston. And it is sealed so that it doesn't leak. And when a hot gas is present in the space adjacent to it, that gas can do work on the piston, and thus you can carry it to the outside world and have a result. In this instance, it's carried by a connecting rod with respect to each piston to a crank with two throws. Shown here is the throw for the displacer piston, and shown here is the linkage to the throw for the power piston. And in operation, you heat this space, you heat this area by focusing solar energy on the walls of this cylinder. So you receive energy on the walls, the air that is there is heated, then it is displaced by the displacer piston. The power piston then is displaced and you do work on the external world, whatever happens to be there. On the generator that you may add, or on the pulley that you may use to move water, or whatever load that you put on it. So in operation, it's amazingly simple and rather easily constructed. It's a displacement piston, a power piston, and the operation of the cycle is simply to add heat, to move the gas to the place where the power piston can be operated on. The power piston moves under the pressure of that hot gas, and you perform a cycle. The next cycle, the next portion of the cycle is to get rid of the heat that's not converted into work. So you can see that in real surface. The portion of the system that is dedicated to getting rid of the heat is the thinned portion. You simply get rid of what wasn't converted into mechanical work as heat and dissipate it to the atmosphere. Or you move it through the walls as heat and dissipate it to the atmosphere. And so then you return a cold gas or the cooled gas for reheating. You can improve on this cycle by putting in between those two operations a device called a regenerator. You can put some chips of relatively inert material, such as stainless steel, or in this low temperature device, even aluminum, and improve the efficiency by putting a regenerator between the two. And that would just look like this. That would be a porous plug of aluminum or stainless steel wire. But those would be the steps. If you wanted to improve the efficiency of the device that you have at home, you can add a insulative cap and add what I've shown here as a method of receiving the solar energy and extinguishing it before it's re-radiated or lost as a reflection. You improve the absorptivity, you reduce the emissivity, and you improve the gain, the solar gain, and improve the thermal efficiency.
Is fluid in the D piston? You got some working, expanding fluid?
No, the D piston is too simple for that sort of activity. The D piston is just a displacer. Think of the D piston as a solid that you move into a space and make whatever was there go away.
If you try to move this, won't the two things go together? Try to move the axle thing.
Well, what's remarkable in this regard, and it looks like, boy, this is too simple to be true. It just couldn't work. So that's why I brought one with me, so we'll go out and work it.
I don't have one.
You've had one?
Yeah.
Did it stop?
It stopped after some time when the heat separation wasn't good enough.
Ah, well, that's exactly right. If this temperature and this temperature become the same or approach each other,
It won't go.
it's done.
Where's the air coming?
That's a big problem. That's right. If this,
Where's the air coming?
that's exactly right. So what you do is you blow on this and get it cool again. Or you put a coil on it and make your hot water. Or do 1,000 things that are better than just doing nothing.
Roy, do you want to talk about the advantages of the free piston Stirling engine as opposed to this design coupled to a crankshaft?
I would.
Okay.
Where's the air come in? It's an air pump, isn't it?
Well, here's the thing. This is a leaky system.
You let it just slide by things?
It slides.
Okay.
You just let it be in there in a while. It'll be loaded up with air, and then you rapidly heat the air up. So much more rapidly than the leaks that it works. But this is a leaky air system. Now you can make it so that it's positively sealed by putting the bellows in.
Then you'd have to pour it, yeah.
And then you'd have to do more by way of controlling the flow of the fluid. But if you did that, it's very worthwhile noting the result. If you do that, you can put in working fluids that carry much more heat than air. Hydrogen carries much more heat, and it's much lower in viscosity, so you have much lower pumping losses by having hydrogen as the carrier of the energy.
My friend built one, and it had a port, and you put a little fire right next to the port, and he would stuck it in, and bring it up, and compress it, and blow it down. It worked like a two-cycle off of that little fire. But it didn't have much power, but it ran.
Well, see, that's the study that everybody goes through. If you have a lot more efficiency and don't take the energy out, you run it too. You know, the thing is, you overheat the material, and they stop. You run them. There was a further development in Stirling's that's very worthwhile to mention. There are many more developments. I could draw all day on developments of what are known as kinematic machines. This is a kinematic machine. But there's another type of machine that's a very worthy device for applying the Stirling cycle. That's called a free piston machine. In the free piston machine, you just take away this portion. You get rid of it and you replace it with a generator or some other way that you take the linear motion as a work function. You could run a compressor, you could do a lot of things, but one good way is to run a linear electrical device, a linear alternator or generator. And if you do, you can get rid of the friction and the cost of materials and the cost of machining the materials of these kinematic devices. Such machines now exist, and they're delightful. They operate at a constant frequency. You can design the system, the dimensions of the system, the masses that are within the system, and the modulus of elasticity of the working fluids, so that they operate at a constant frequency. You can have them operate at a constant multiple of 60 hertz, and they won't go off of that until they just don't work at all. If they're on, they are 60 hertz. And that's a very nice way to operate your electrical system if you're running the appliances interchangeably with the grid. A 60 hertz synchronous machine.
Where would you find such?
Cummins has licensed the design for free piston and are now offering, in competition with diesel gensets or photovoltaics, a free piston Stirling system. A dish and a free piston engine with an alternator built in. And if you want to buy one, they have them for sale.
Who is that?
Cummins
What
diesel.
kind of price are we talking about?
Well, they're competitive with photovoltaics.
What size range do they?
5 kW. Or you can put 3 together and have 3-phase at 15 kW. 3-phase, which would be an advantage on their single phase.
You're using what?
Let me catch one right here. I want to be sure we ran a lot of questions in front of this guy's question. I want to be sure we answered this question. Did we get the...
Oh, you did? I just have another question.
All right.
Would you give an address for that system, that
Cummins?
free piston? The name and address?
It's Cummins Diesel. Cummins, C-U-M-M-I-N-S. Cummins Diesel.
They're in Columbus, Indiana.
Yeah, you know, they make diesel engines.
Can you get it for real goods?
Can you get them through real goods? And the question's been asked that you can't get, but you can certainly get them from the company. Please.
Okay, seems like anybody that's taken thermodynamics, there's the standard steam turbine. How does this compare to the standard steam turbine? They both have to operate under the laws of thermodynamics, so what's the inherent advantage of the Stirling?
The inherent advantage of the Stirlings compared to the Rankine cycle devices is simplicity. These can be made in modular units that are extremely quick to respond to any solar energy that's available. If solar energy comes on and goes off and what have you, the Rankine cycle is troubled because you have to go down and pump up the system and heat up the boiler and what have you to get it running again. This system operates in a few seconds, as we'll demonstrate. That's a very distinct advantage. They also operate with a higher thermal efficiency. They more closely approach the Carnot cycle than the Rankine cycle. Now you can do a lot of things with the Rankine cycle. Look, don't forget that you could run a hydrogen-fired gas turbine, dump the waste heat to a water load, make steam and run a turbine, so you'll have a Brayton cycle over a Rankine cycle and get a very good approach to the Carnot cycle. You fill out the curve much better. So that's a very good thing to do. The key to that is to use hydrogen as the fuel in your gas turbine. Hydrogen in the gas turbine is a very, very attractive way to operate. It simplifies the gas turbine. Instead of having heat transfer from a fossil fuel to the air, you simply burn hydrogen within the air and produce very high temperature steam. And the overall cycle has a much higher starting temperature and a much lower finishing temperature because of the Rankine cycle, or the hybridization of two cycles, or combining of two cycles, than if you only ran one or the other. So that's a very good way to do it. This, however, starts at a higher efficiency than either of those two cycles. And you still have the opportunity to do the same thing here. You could piggyback on the top of this a gas turbine and dump the waste heat of the gas turbine to this and have a higher overall simplicity and cycle efficiency in that combination too. So those are the comparisons. But the Department of Energy has so recognized these advantages that they now have a request out. No upper limit on amounts that they would match. If you want to bring $100 million to the party, they'll match $100 million to make this happen for utilities. So the lights have gone on for them with respect to this technology.
When did that happen?
Just this happened. Just now.
Really?
It's 1 month old.
Does that breathe new life into the big solar energy brand concept?
Surely does. It sure does. It breathes new life into the concept of taking land that has low value at present and making it worth $2,000 an acre every year without end in productive use. And if you don't like what you have in 20 years, you can get rid of it. These systems can go away without residue. And in the meantime, you don't hear them, you don't smell them, and you don't need to see them unless you have a habit of going to look at worthless land right now. They're making that contribution in the form of a no-holds-barred fund matching program.
He's asking whether someone can make the contribution, the matching contribution in the form of donating the land.
Oh, yes, that can be part of the consideration. Yes. Yes, that can be part of the consideration. It can't be all of it because they can say, all right, we'll put up land too, then all you have is land. You have to have some do-re-mi in there somewhere to pay for the job development that this means. The Department of Energy is looking for job development.
Not having some creative financing where you buy half the land at nothing and the other half you buy at double the price of the rest.
Yeah, absolutely. See, there's a lot of ways to do this, and they're very receptive. So long as you buy American, that's one of the rules they have in this. So long as you create jobs, that's what they're looking for. And so long as you come up with an efficiency and a capital cost that pleases the utilities, and they place orders. The rules are you have to get this in a acceptable to the utility form as a result of their participation.
Is it state or federal law?
This is federal. So it's a very favorable thing that's happened with respect to this technology.
Do you have information on that in your booth?
Yes, we do. Please.
Is there some guarantee working in the DOE offers that the ideas will actually be used as opposed to get somehow buried when if utility companies decide to invest it in their profit mode?
Well, that remains a question. It does not address that potential contingency. That remains a question. And I think that remains a question to the consumers that we are. And I think that remains a very important question to the educational system that we are part of in our educational activities. I feel a very large responsibility to you, to the public at large, in providing these alternatives as considerations that you can make for your purchasing purposes and for your own energy independence if you choose to make it that way and leave the utility out of the picture. I think that that's another alternative that could be discussed and could well make a very different America at some 20 or 30 years point in the future.
Make your own utility.
You could be your own utility. There's much federal support right now under PURPA laws for you to be your own utility and to sell to others. I don't know if you want to investigate that, but you might look up the Public Utility Regulations Act and see what it requires for you to be a qualified facility or an independent power generator. But those are very favorable for private generation. Please.
I just want to make a comment of the idea of active demographic units. In other words, we wait until corporations collect demographic information on us and they make their marketing decisions based upon that. Yeah. And I think what you're suggesting is be active and just say to Cummins, Diesel, or whoever, we want this.
Absolutely. You do not need the federal government to help you go to Cummins right now or to Detroit Diesel. They're making one too.
Right. Or you don't even have to wait for them to, typically their market research is based upon demographic material. So if you're saying, hey, look, we're going to short step that process.
That's right. And I really sincerely know this to be the way you'll get a quicker response from industry and you'll make a healthier industry than if you wait for the government to do it for you. If you go to Detroit Diesel right now, or if you go to Cummins Diesel right now, or Caterpillar, go to somebody who's manufacturing power plants and you say, I don't want the one that stinks. I'm sorry, but I don't want the one that stinks. I want the one, I can't remember the name, but I want the one that runs on renewable energy, and I want it now. You'll get it. But you've got to make it clear to them what you want.
So you think you'll change and make what you want?
I do, absolutely do. I make my living as a manufacturer. Let me just say, I make my living as a manufacturer. I manufacture welding products.
Yeah.
And I really listen to the customers. My product is entirely customer shaped.
You're unique, though.
It's really dumb for me to tell them, well, this is what I want you to have. I've got to say, what do you want?
Well, that's the feedback loop that isn't happening, is that people wait for the manufacturer to create products that they may or may not want.
Look, I tell you, I think we've lost our place as consumers. We've become dumb consumers.
Well, yeah, but I mean, if you look at the record now, consumer confidence is down, so I don't think they're starting to wake up a little bit, because they're stopping to buy.
You know, here's the automobile companies that have lost market share for ignoring that question are wishing they would have asked.
Yeah.
They're wishing they would have asked. I think that now's the time to capitalize on that condition.
Yeah, because I mean, there's so many people that are looking for work. I mean, that alone, could spark a whole revolution.
I really believe that we're sparking a revolution. It's a renewable resources revolution. What is happening is that we're entering a renewable resources revolution. We're transitioning from the lessons that we've learned in the Industrial Revolution to the renewable resources revolution. Whether you like it or not, we're doing it. We're having to do it. We're not going to be able to meet the expectations of the third world without it. It's the largest population, the largest market. That market has held up its hand. And that market is saying more often than we are, we don't want the one that stinks.